What is system administration? Once upon a time, Unix ran only on large dinosaur minicomputers like the Digital Equipment VAX series. They lived in special air-conditioned rooms and served compute resources to dumb terminals all over the company or university that owned the machine. The system administrator's job was to keep these sometimes cranky machines running smoothly and to be the human interfaces between the machines and those who would use them. Our job was to make these machines serve the people we worked for. It was a strange job, where a new hire, or in my case a student employee, had more privilege in the system than a department director. Today, there are Unix and Linux systems that fit in your pocket. Your iPhone runs iOS, derived from BSD Unix, and the Android operating system is based on Linux itself. In the foreseeable future, they'll be in your watch. There may be a Linux computer on your desk at home. Your kids may have Raspberry Pis that they play with. These too are Linux computers, and all of them more powerful than the dinosaur mini computers I used to run. The massive server farms of the cloud are most often Linux-based. Of course, they need system administrators, but so does the Linux machine on your desktop, the Android phone in your pocket, and all the other Linux and Unix-like operating systems that literally surround you. The job's easier than it used to be. Hardware is a lot better and unimaginably cheaper, but the numbers have multiplied beyond imagination. System administration isn't a skill just for nerds like me anymore. These machines are as ubiquitous as cars, almost as much as air. Like driving or breathing, system administration is a skill everyone needs now. As Linux proliferates, the need for system administration skills proliferates with it. You have to understand what these machines can do, what they are doing, and how to take control over them. In this new age, Linux system administration skills are no longer just about making machines serve other people. They're also for controlling the machines that serve you. What to expect from these videos? You may have seen that ad in the back of some old comic books, where the skinny kid bulks up into this big muscular guy in just a few short weeks after buying their products. This series of videos is not like that. There's no way to give you the benefit of years of study, practice, experience, and caffeinated soda in any number of videos, and even if I could, you still wouldn't know everything. It changes. Here's what you will learn. You'll learn all about the terminal environment and how to use it. It's the least common denominator between Linux distributions, and most of the best tools are there. You'll learn about file systems, probably more than you ever wanted to know. File systems are the heart of Linux, because in Linux, everything is a file, and the whole security model is based around files. You'll learn about the Linux kernel, and processes, and daemons, and virtual memory, and file security. You'll learn how accounts work, and how they're put together, and what exactly root is anyway. You'll learn mechanisms, like what the boot cycle looks like when it works properly, and how to read Dmesg and Logfiles. And you'll learn some strategies for when the system hangs, when the GUI won't start, when the file system turns up corrupt, and when it's time to roll up your sleeves and reinstall. It's not everything, not by a long shot. Here's the thing. Being a good system administrator does not mean you have to know it all and that you have to have it all in your head all the time. A friend of mine, himself a career Unix and Linux system administrator and a world-class guru, admitted to me once that he thinks of himself as a generalist, someone who knows how these systems work broadly and has the experience and the expertise to understand what he needs to know and then to look it up when he needs to know it. That comment has been my working plan for this whole series. Linux is big. It's been adapted to hundreds of platforms and thousands of jobs, from mission-critical cloud servers to telemetry for stuffed bears tied to weather balloons. Thousands of talented programmers work on it every day, extending it and evolving it, but they stick to the Unix-like underpinnings that make Linux Linux. With these videos, you'll understand what these underpinnings mean and how to use them. These videos will give you a place to start as a Linux system administrator. A quick history lesson. Unix was born at Bell Labs, a division of Bell Telephone, which was the telephone company up until it was broken up in the 1980s. The largest remnant of Bell Telephone today is AT&T. It was the early 1970s, and mini-computers were changing the scene. Mainframes had been around for a while, and people understood how to use them. You wrote your program and data, and you put it on punch cards. You handed them to the nice operator, who put them on a tape. And when your time slot on the computer came up, they loaded your tape, ran your program, spun the output off onto another tape, and the nice operator printed your results from that second tape. Minis, though, were different. They were smaller, for one thing. Instead of taking up the whole room, they only took up a wall or so, like a row of file cabinets. They were cheaper, too. You could get a Mini for less than $1 million. And they were also more interactive. A user could sit down at a terminal, which was a printer or a screen and a keyboard, and communicate directly with the minicomputer. It was obvious from the start that a minicomputer had to host multiple users at the same time. Minicomputers were where the computer revolution really took its cause to the masses. Unix was born to do this. It was born to share expensive resources with large numbers of users. It was born to do, or appear to do, multiple jobs at the same time, a process called multitasking. It was born with security to keep my files separate from your files and my memory separate from your memory. In 1974, Unix went to college, where it landed in the computer science department at the University of California, Berkeley. When it emerged in 1978, it was different. There were more utilities, different editors, an entirely new kernel, Berkeley sockets, and perhaps most importantly, a better implementation of TCP/IP, the backbone protocol of the Internet. That same time frame saw the explosive growth of ARPANET into the Internet of today, and then came the web. When Tim Berners-Lee invented the World Wide Web, along about 1989, he ran the first server on a Next workstation running NextStep, which is not only a Unix-like operating system, but formed the basis for Mac OS X and iOS when Apple bought Next and rehired Steve Jobs in 1996. You may know the rest of this story. In the 1980s, Richard Stallman and GNU made a name for themselves by writing replacements for most of the Unix user space, from the C compiler to the shells to the tiniest utilities like ls. But even today, in 2015, their kernel still isn't finished. The bottom line is that in 1991 or so, when 32-bit 8386 computers showed up with the power and memory of minicomputers that came before them, Linus Torvalds wrote a Unix-like kernel and gave it to the internet for free. When that kernel was combined with a GNU user space, Linux was born. So why does this ancient history still matter? The concept of user space, kernel space, superusers, and root all make a lot more sense when you picture 20 or 30 of us using the machine at the same time, only one of whom is authorized and competent to maintain the system. More importantly, the software tools, security concepts, and most of the system's control files are still the same, or at least called the same thing. It's important because Linux and Unix-like operating systems can be obtuse. It helps to know that gawk, which is a file utility, is the GNU equivalent of awk, and that the word awk has nothing whatever to do with what the program does. It stands for the initials of Aho, Weinberger, and Kernighan, who wrote it. Likewise, Biff, the original program that told you you have mail, which can still be installed in modern Linux, was named after a dog at Berkeley who barked at the mailman. As a Unix-like operating system, Linux inherited all of this history. It hasn't clung to anything that's not useful anymore, but the concept behind its virtual memory system goes back to those days of $50,000 a meg. The commands are still the way they are because they made sense on an ADM3A terminal. In other operating systems, out-of-date memes like these would be signs that the OS is past its prime. For Linux, they're its strength. They're the consistency that allows it to move forward without abandoning software. You'll trip over this historical rubble from time to time. It's inevitable. But these mechanisms are well understood and well tested. Welcome to Linux. In this video, you'll learn about terminal emulators and bash. You'll learn what a terminal emulator is. You'll learn where the terminal emulators are in your distribution of Linux. You'll learn the relationship between terminal emulators and the command shell, and you'll be introduced to the bash command shell and the bash prompt. This is a terminal, a keyboard, a screen, serial communications hardware, simple graphics, and text. This is how you communicated with Unix and Unix-like operating systems for most of their history. Even though Linux was born on microcomputers with video cards, keyboards, and mice, even though this particular Linux system is running in a virtual machine, it still has all the serial terminal anatomy. Most of the best tools for Linux system administration expect nothing more. When we talk about terminal emulators, they are software to emulate this specific terminal, a digital equipment VT220 or its predecessor, the VT102. Most Linux distributions make the terminal emulator fairly easy to find. In Ubuntu with the standard Unity desktop, it's under the search icon, and it's right up front in Applications. In most Ubuntu variants, such as Xubuntu, Lubuntu, and Ubuntu GNOME, it's in Applications Accessories. In Mint and Ubuntu with Cinnamon, it's in the shortcuts on the left. In Kubuntu, with the KDE Plasma desktop, look in Applications, System, Terminal. It's called Console with a K. In Fedora's GNOME 3 desktop, it's right there under the Activities shortcut. Whatever terminal software you're using, put it someplace easy to find, on the desktop, in the dock if you have one, on a panel launcher. You'll be using it a lot. For the rest of this video, I'll blow the terminal window up to fill the whole screen with nice large print to make it easy to read. When you start your terminal software, it takes the place of the hardware terminal, the serial hardware, and a Linux service called getTTY. It creates a text window, interfaces with the keyboard and mouse, and invokes a command shell. We'll be using bash. This is bash. In case you've never used one before, a command shell is a program that reads commands from the terminal and sends results back to the terminal. Bash is a command shell. Bash is also a programming language. Bash programs, like any other command shell programs, are called scripts. Your Linux system has lots of scripts that it runs when you start it up. Nearly all of them are written in bash. They're easy to modify, human readable, and maintainable with nothing more than a text editor. There are dozens of command shells, some of them dating back to the 1970s, but bash is the most common among Unix and Unix-like operating systems today. So before we start telling bash what to do, we should look and see what bash is telling us. For this demonstration, I'm going to use a bunch of commands I haven't introduced yet. We'll get to them all. The prompt here tells us some very useful pieces of information. First, it lists what account I'm logged into. Right now, I'm logged in as JRS. That's my account. If I change to the root account, you can see that bash tells me. This is important. The root account has a lot of privileges and can turn your Linux computer into an expensive brick with a single command. So let's get back to my account. The next thing the prompt tells me is what system we're on. Vubu is the host name for the virtual Ubuntu machine I'm using for this demonstration. I gave it that name. There's nothing special about it. When you use SSH to log into other Linux computers, or if you use virtual machines, the host name becomes very important. After that is a colon, and after that is a tilde. The tilde means I'm in my home directory on Vubu. If I change directory to /var/log, for example, bash tells me. The $sign is a very old traditional way for bash to tell us that our input is required. It also changes if we switch to the root account. Every Linux distribution has its own conventions for what the bash prompt should look like. This is Fedora. The prompt will usually give you the same information, but it may be in a different order. It's important to remember that bash is just another program. You can call it from within a bash shell. Just type bash and press return. The prompt may change, or not, depending on how your bash configuration files are set up. The exit command terminates the bash shell. Since we've started 3 bash shells, in addition to the one that was started for us by the terminal emulator, we have to type exit 4 times. The first 3 exit a bash shell and hand us back to the previous one. When we exit the bash shell our terminal emulator started for us, the terminal emulator usually exits too. There's really only one important difference between using a terminal emulator and a real terminal, aside from not maintaining a 35-year-old piece of equipment. Real terminals get what's called a bash login shell. It prompts you for the username and password, sets the home directory to your account, and hands you off to bash. A non-login shell is what you got when you started your terminal emulation software. They don't ask for username and password. They assume you've already logged in through the GUI. This seems like a trivial thing until you set out to change your personal bash configuration. You have to know which file to edit. Linux distributions vary on which one is the right one and whether they know the difference between a login shell and a non-login shell, and where in your account they actually put the files. If you want to modify them, you have to look up the specific locations and files for your distribution of Linux. For now, I suggest using bash in its default configuration. Linux directory tree navigation. In this video, you'll learn to navigate the Linux directory tree in the terminal environment. This is the equivalent of pointing and clicking on various folders and files in the file browser. It takes some explanation if you're not used to it, but it's very quick, and it's very powerful, and it works even if the graphical user interface is broken. Some vocabulary. A directory is the same thing the GUI world calls a folder. A volume is what we used to call a drive or a disk or even a tape. Things are more complicated today, and volumes can span multiple drives, disks, or even tapes, so we'll use volume to mean that level of the storage system. If it helps to think of a volume as a physical disk, that's fine. The word file system has several meanings. We're going to use it for one thing: the data structures on the volume that allow the data to be stored and retrieved. These are created when the volume is initialized/formatted. Modern Linux usually defaults to ext4, although there are lots of other options. Let's talk a minute about directories and what they are. A directory is a file-like part of the volume's file system that contains a list of other files and information about how to access them on that volume. In the Linux ext4 file system, each entry in the directory contains the file name, access information for the file's data, the inode number, the file's type, access information about the file's parent directory, and other stuff for the directory data structure to make it fast. You can have directories inside other directories until they form a tree-like structure. This is called the directory tree. The bottom of the tree is called root, or a slash with nothing in front of it, and each branch is a directory. I've installed a utility called tree on this Linux machine to show you what I'm talking about. The tree starts at root, here. In the root directory, you can find the boot, bin, and etc. directories, which contain system software and configuration files and the system bootloader. You can find the home directory, and in that is my directory, JRS, and in that is every directory I have, and so on. In more complex systems, a given directory may, in fact, be a mount point. I've hooked an old USB floppy drive to this virtual machine. When I put the floppy into the drive and click the floppy icon, Linux will automatically create a directory in /media/JRS and connect or mount the floppy drive to it. It will use the volume's name as the directory name and the root directory of the new volume as its contents. The floppy just became part of the directory tree. I can use it the same way I use any other directory. The only difference will be speed. Floppies are slow. What are inodes and the inode table? Like the directory table, the inode table is a file-like part of the volume's file system. Each inode table entry contains the location and size of the file's data, the file's access control permission information, the file owner's ID, the file type, and the number of hard links to this inode, and a lot of other stuff that's mostly important when you're writing file system drivers. Unix and Unix-like operating systems were designed to be multitasking, that is, to have multiple things happening at once. Suppose program A is reading a file. Program B, running at the same time, deletes the file. What happens? The directory entry gets deleted, and the inode table is updated so the number of hard links to that inode is 0. But the program can go on reading the file as usual because it has the inode of the file. The inode still exists, and the file won't be overwritten until program A lets go of it. Normally, we'll look at directory and inode information together. Let's take a short break here. When we come back in the next video, we'll look at tools for navigating the directory tree, ls, pwd, and cd. Picking up where we left off, let's look at the tools available for navigating the Linux directory tree. We'll start with ls. In the demonstrations I've made of directories and files, I've thrown around a lot of commands. The truth is, you really need about 3 to navigate the Linux directory tree successfully. Those commands are ls, pwd, and cd. We'll start with ls. ls lists the files in a directory. If you use it by itself, you get a list of the non-hidden files in the directory you are in. This is my home directory, the branch of the directory tree where all of my files and directories are. You can see them on the screen. In this case, white for files, blue for directories. ls can color code the file types, and most Linux distributions set it up that way. The colors vary from system to system, and some systems may use no color at all. Obviously, if your terminal software, your version of ls, or your eyes don't do color, there has to be another way to tell the kind of file you're looking at. There's another flag for ls that does exactly that. It's called ls-l. ls-l gives you a lot of information at a glance. You'll get used to reading it instantly. The first letter is the file type. The most common entries you'll see here are D or minus. A D is a directory, and a minus is a plain file. There are more obscure types, such as P for named pipes that let 2 programs communicate with each other directly, S for socket, which is like a named pipe, except that it lets you send other types of data, and C or B for the 2 flavors of device files, character or sequential, and block or random access. If there's an L, like here, you're looking at a symbolic link, which is a name that points to another name in the directory tree. ls-l also tells you what file that link refers to. Symbolic and hard links are a subject we'll get into later in this video. ls-l also gives you the permissions of a file in 3 groups of 3. We'll get into permissions later. For now, just remember that there are 3 groups of permissions. The first for owners, the second for group members, and the third for world. And the permissions are read, write, delete, and execute. The last item ls-l gives you before the file name is the touch date. This is the date the file was last modified or touched. If it has a time rather than a year here, it means the file was last touched this year. If it lists the year as 1969, it doesn't mean the file dates back to the Stone Age of Unix. It means the touch date wasn't set, and therefore is 0. ls-l also gives you the size of the file in bytes. When Unix was young, this made sense. A file might be a few kilobytes. With file sizes into the gigabytes and terabytes, it's hard to read. Fortunately, there's another flag we can add to ls-l, the H flag. H stands for human readable. So ls-lh reduces the number of bytes to the nearest unit. If it's less than a kilobyte, or kibibyte for the pedantic, 1024 bytes, it will show the number of bytes with no unit. Kilobytes are capital K, megabytes are capital M, gigabytes are capital G, and so on. ls-i will give you the inode number of the file. You can combine other flags in ls and most commands, like ls-alh, to get all files, long info like we were just talking about, and human readable. The order of the flags isn't important, so ls-lah and ls-alh do exactly the same thing. As we've seen, the Linux directory tree can get pretty complicated. It's always a good idea to know where your shell environment is pointed before using rm or any of the shell's more destructive commands. pwd is the tool for the job. It stands for print working directory. If we type it, we can see that we're in a directory called /home/jrs. That's / for root, home for the home directory, and jrs for my directory in home. pwd takes two parameters, -l and -p, and they affect how pwd displays symbolic links. The default behavior for pwd is -l for logical. This means that it shows the symlink we used to get here. If we use pwd-p, however, it shows us where we really are in the directory tree. A symbolic link is a directory entry that is an alias for another directory entry. They can go anywhere. If I'm using the /var/log/apt directory a lot, and I don't want to type it out, I can create a symbolic link to it called logdir. That's the original directory. There's my new link there. You can see that it points to var/log apt. And you can see that logdir now contains the contents of /var/log/apt, or more precisely, it takes us there. Because symlinks point to a directory entry, if the original file is deleted, they will fail. And there you can see that it is failing. It's no longer giving us the contents. A hard link references the same inode as another directory entry. It's a second name for that file. Because hard links reference specific inodes, they can't span volumes, but they will become a given file's only name if the original is deleted. As you can see, they point to the same file content. However, if we delete test1, we still have the same content, but it only has the one name. cd is the simplest command. It stands for Change Working Directory. Let's take another short break here. When we come back in the next video, we'll cover cd and Linux shortcuts. Let's pick up where we left off and look at cd and Linux shortcuts. cd does not take any flags, and it only takes one parameter, the directory you want to go to. Linux provides some shortcut directories you can use, and they'll work with cd. cd tilde takes you to an account's home directory. It's a really useful shortcut because different distributions put their user accounts in different places. On this demo Ubuntu system, my home directory is /home/jrs. It's the same on Fedora. On my Mac, which also runs a Unix-like operating system, it's /users/gim. All of them will go to the right place if I type cd tilde. If you don't specify which account, it will take you to your own. If you are logged in as root and you don't specify an account, it will take you to root's home. To specify an account, just put it right after the tilde. Note that some directories will require privileges just to see. Remember, Linux assumes that multiple people will be logged in using the system at the same time, and it will do its best to protect the users from each other. cd takes you up one directory level toward the trunk of the directory tree. cd takes you to the same directory you're already in. This shorthand isn't very useful for cd, but there are times when it's absolutely invaluable. So now you know what the Linux directory tree is and how to get around in it. Go ahead and explore your Linux machine's directory tree. It may be organized a little differently than my demo machine, but it'll all be pretty familiar. It won't be long before cd, ls, pwd, and their various flags roll off your fingertips without conscious thought. The directory tree will simply be as familiar as the road you live on. root over there, etc. rc.d over there, and my place over here in /home. When you've used these commands a while, it's actually hard to go back to the slow click, scroll method that GUIs use. Files and file manipulation. From the terminal environment, there are 6 basic things you can do to a file. You can create it, you can edit it, you can copy it, you can move it or rename it, you can view it, and you can delete it. File manipulation is fundamental to Linux system administration. In this video, you'll learn to do all those things. To Linux, everything is a file. This bears repeating. To Linux itself, everything is a file. Even though directories and inode tables are somewhat different for speed, to Linux, they are files. Physical devices are files. Everything is a file. Here, look, I'll show you. This is the /dev directory. All the device drivers for the entire system live here. Every one of these represents a physical device. Here's memory. Here's floppy disk. Here are all of our various possible terminals. You can send data to them like files. You read data from them like files. Linux treats them like files. They are files. That's the Unix way, and that's how Linux does it. Keep this in mind. It's a very important concept to understand how Linux works. So, what is a file? When we talk about a file, we're using an analogy. What we're really picturing is a physical stack of papers all bundled up into a file with a name on it. That's actually not far from the truth. A file is really a combination of things. It's an entry in the directory table for the directory it lives in. That entry, along with other things, includes the inode number. The inode number is an entry in the inode table. The inode table entry gives you, among other things, the addresses of the data blocks in the file. So, what is a data block? A data block is a sequential series of storage addresses on the volume. One block is the minimum size for any file on that file system. Block size is set when you initialize or format the volume. In the ext4 file system, the default size for a block is 4 kilobytes, or kibibytes if you are pedantic. But they can go from 1 kilobyte to 64 kilobytes. So, what does a data block look like? Well, like this. Here's a single 4K data block displayed using the hexdump utility. We're not going to cover this utility, it's not something you use every day, but it does let us see the raw data byte by byte in 2-digit hexadecimal numbers. This is what Linux sees. These are the offset from the beginning of the file. These are the bytes themselves, and here's what it translates to in human readable form. Blocks come in groups of various sizes and extents and whatnot. Most of this is for file system performance. It's set up and maintained automatically and not something you as a system administrator need to deal with regularly. This is good because file system architecture and programming are whole subjects unto themselves. There are 2 file name traditions in the terminal environment that GUI applications often ignore. In the old days, you could call your files whatever you wanted, and if you told a program to open a file, it would try. You could cat executable programs to your screen for page after page of gibberish until your terminal froze. As always, things are more complicated now. It is traditional for file names to have a period at the end and some kind of extension to tell the user what the file is. The other tradition is that Unix and Linux file names do not contain spaces. Since 1984, GUI app designers have hated that. So when you're at the command line and you run into a file that has spaces in the file name, you can use a \space to tell bash that there's a space there. This works for any character that is special to bash and shouldn't be in a file name. If there's more than one in a row, you can enclose the file name in single quotes to prevent bash from trying to interpret the file name into commands. We're going to take a short break, and when we come back, we will talk about creating files with Touch and Nano. In our last video, we talked about file name conventions. In this video, we'll talk about creating files and editing files. The easiest way to create a file in the terminal environment is the touch command. As you can see, we only have one test.txt. Let's make another. Note the date on the file. That's the file's M time, the last time it was modified. That's coming off the inode table. Touch always modifies a file, even if it creates it. The next easiest way to create a file is with a text editor. We'll use Nano. So, why should we learn a terminal editor? Text editing is one of those things that GUIs actually do better than terminal applications. But it's still useful to know at least one terminal mode editor to use on servers that don't have GUIs or where the GUI is broken. Why Nano? The most traditional editor is VI. It's present in literally every Unix-like operating system I've ever encountered. but most Linux systems come with Nano. It has some important advantages. It's more modern than VI and makes use of advanced terminal controls. It's less complicated than Emacs, which is the other choice. The big advantage is that it tells you how to do the most common tasks across the bottom. This is very useful on an editor that you don't use every day. If your distribution doesn't come with Nano, like this Fedora virtual machine, it's worth installing it now so that when the system is so messed up that it won't boot all the way, Nano is already on it. If you already know VI or Emacs, feel free to install and use either one. Terminal window text editing has a couple of conventions that are alien to GUI editors and their users. Nano has buffers. In Nano, a body of text is in a buffer. A buffer can be copied in from a file or copied out to a file, but the text you can touch is in the buffer. This is important because if you don't tell Nano to save that buffer to a file, it doesn't. So we've edited this file. You can see that I've put text in it. I tell it to exit. It asks me if I want to save the modified buffer. If I answer no, the data goes away. Pressing Ctrl-O explicitly writes the file. If you're making a lot of edits on a system that isn't stable, writing frequently will save you a lot of headaches. It asks for a file name, even though we specified one when we started Nano, in case we want to change our minds. You can read another file into your buffer with Ctrl-R. Nano will insert the contents of that file where your cursor is right now. You can search for text in the current buffer with Ctrl-W. And you can repeat it simply by hitting Ctrl-W again and pressing return. The search will wrap. So now that I'm at the bottom of this file, if I search again, it will wrap to the top. Ctrl-backslash will replace text in the file. It asks for the old text and the new text. If it finds any occurrences of the old text, it will ask you if you want to replace that or if you want to replace all occurrences at once. And we do. As with search, this command will wrap from the bottom of the buffer to the top. Here's where buffers become really important. There's a second buffer in Nano called the cut buffer. If you move the cursor to a line and press Ctrl-K, it takes that line out of the main buffer and puts it in the cut buffer. If you want that line somewhere else, move your cursor there and press Ctrl-U for uncut. Nano has a lot more options than these. They're listed if you press Ctrl-G. There are two types of link. The symbolic link, which is a directory entry that refers to another directory entry, and the hard link, which is a directory entry that points to the inode table entry of an existing file. LN stands for link. It creates the links between files. It takes two parameters. The first is the file that already exists. The second is the name you want the link to have. It also takes a flag, -s, to tell it to create a symbolic link rather than a hard link. If we look, we have a file called test1 and one called test.txt. So I'm going to create a link from test1 and call it test2. I'm going to make it a symbolic link. There's nothing actually in this file. If I remove test1, you can see that even though the test2 link still exists, it doesn't point to anything. By contrast, if I create a hard link called test2 to test1, and I remove test1, test2 is still here. Let's take a short break. When we come back, we'll talk about moving and renaming files. Welcome back. In our last video, we talked about copying files. In this video, we're going to move on to moving and renaming files. All of this will be done in demos. You can copy files and directories with the cp command. To copy a file into a directory, you use cp, file name, and the directory name. To copy a directory, you copy the directory name to another directory name with the -r flag. As usual, there are lots of flags, but only one other useful one, and that is -l. It causes cp to follow symbolic links and copy those files too. Hard links are real directory entries, so they're copied by default. Moving files from one directory to another is a fairly simple job, and it has a fairly simple utility called mv for move file. What I've just told it to do is move test1 to the shorthand for one directory closer to root from the one that I'm in. And you can see it here in my home directory. You can also use mv to rename a file. It is, in fact, the same process. Move only has a small number of flags, and only one is really useful, and that is -i. By default, If you move a file into a directory where another file has the same name, or you rename a file to the same name as another file, that other file is overwritten. It's gone. You can see renamed test1 has been renamed to test3, and the original test3 is gone. mv-i asks you if you really wanted to do that before doing so. Do I really want to do that? No. If you do, type a Y. There are two main commands for viewing text files in the terminal environment, cat and more. Cat is a powerful command. In addition to displaying the file, it can display multiple files in sequence. It can show hidden characters such as line feeds. The $sign here is a hidden character. If you need to know what special characters are in a file, an easy mnemonic for the flags is that you take the cat to the vet, cat minus VET. Cat has many flags, but with multi-page files, it's not as useful as one might like. Enter the more utility. More takes a file name and displays the file page by page. Deleting files, RM, and wildcards. This is the dangerous one. This one single command throughout Unix and Linux history has caused more mayhem than any other. This command deletes files. It is called RM for remove. The simplest form of RM is also the safest. You give it a file name, it deletes the file. RM won't delete directories at all. That takes a special command, rmdir. If the directory is not empty, rmdir will fail. Pretty straightforward. It's flags and wildcard that make RM powerful and dangerous. The asterisk. In Linux, as in all Unix-like operating systems, the asterisk is a wildcard for any string of text, or more precisely, all strings of text. If those strings are file names, it will match all the files in the working directory. If you specify some letters in the string, you can limit the wildcard's matching a little. So for example, ls*.text will not match myimage.jpg because the ending of the string is not the same. This is the tip of a much larger Linux iceberg called regex, or regular expressions. But for now, the wildcards are all we need. Okay, RM. RM with wildcards. All the text files are gone. Note how all the files in our working directory are gone, but the subdirectory is still there. That doesn't seem that dangerous. RM takes flags. The most common, the most dangerous, is -R for recursive. This will tell RM to dive into any directories it finds and repeat the command it was given. Note how both the directory and all the files that were in it are gone. RM will remove directories when it has the -R flag. It's great for cleaning up some deep directory tree with thousands of files. There is one safety mechanism in RM. It stops on errors. Naturally, you can suppress that behavior with a flag. The flag is -F for force. That means do whatever you were going to do and don't prompt the user. When you type RM-RF, you tell RM to remove everything in the working directory that matches the file name pattern and in every subdirectory thereof, and don't complain about errors. Therein lies the danger. If your working directory isn't where you thought, or if one of those directories is really a link to / or /user/bin, or some other mission-critical area of the directory tree, you can cause mayhem. In the old days, if you caught your error fast enough, you could hit Control-C and stop RM before it got everything. With today's SSDs, you can't stop it. But here, I'll show you. Some versions of RM will give you a warning if you point a recursive RM at the root directory. Don't count on this. In this particular setup, this virtual terminal is so slow that it will slow the actual process down. So I am redirecting RM's output to /dev/null. In short, I have gone to some lengths to make this happen, but this virtual machine is doomed. This command tells it to recursively dive the entire directory tree, delete everything, don't warn me, don't protect root, don't send me any output at all. If I had a backup drive mounted, it would dive into that too. Linux will do what you tell it no matter what, so be careful using RM-R, particularly with privileges, and doubly with wildcards. Pipes and redirects. In this video, you'll learn about standard in, standard out, and standard error. 3 standard files, sometimes called streams, which all terminal programs use to communicate with the terminal itself. After that, you'll learn about pipes and redirects, 2 methods for sending the contents of those files to other programs or files on the fly. Every running terminal program or process in a modern Unix-like operating system has at least 3 files: standard in, standard out, and standard error. Standard in is fed from the command shell when you type data in and press return. Standard out is copied to the terminal by the command shell. Standard error is also copied to the terminal. These three files are numbered 0, 1, and 2, which becomes much more useful when we talk about redirects. In Linux, everything is a file, it's true, and these files are handled like normal files, but they're generated on the fly by a running program. They end only when the running program ends, or when they get an end of transmission character, EOT, which you send from your terminal with Control-D. So what is a pipe? Pipes, in Linux, are a specialized type of file. They are used so that one running program or process can have its standard out connected to the standard in of another. Two processes connected this way are referred to as a pipeline. As with some types of real plumbing, pipes only flow in one direction. That's great, but what can you do with it? Pipes are fundamental to the command line because they allow you to chain tiny programs like ls and more together. You can do that with the pipe character, which is somewhere on your keyboard, although it varies greatly where. On all of my keyboards, it's the shifted / key. Here's a demonstration. That's a lot of files. And remember, in the old days, your terminal didn't scroll back. Instead, we'll pipe the output of ls-l to the input of more. Hit the spacebar to go to the next page. Redirects are similar to pipes, but instead of connecting two processes together, they connect one of the standard files to another file. They are done in bash with the greater than or less than character, or two of them if you want to append the current data to an existing file. Consider cat once again. If we redirect the output of cat to a file name, we get a new file. Note that single redirecting always erases the target file, so if we do this experiment again, we'll see exactly the same result. If we redirect and append the output of cat to an existing file name, any existing content will be preserved and the new content will be added at the bottom. And you can redirect both directions at once. Redirects aren't limited to the output of programs. You can also redirect the input, and you can redirect both ways at once. You can even use cat and a redirect to create a new text file right from your terminal. No editor required. Redirects default to directing the standard out of a running program to a file or the standard in of another running program, just as pipes do, but you can be more selective. If you put the number of the file you want, 1 for standard out, 2 for standard error, you can specify which one you want the redirect to affect. Imagine for a moment that you want to ls the entire directory tree. You know that you don't have privileges to read some of those directories, and you'd like to see which ones those are, in addition to seeing what files you can see. We could do this. These are the ones that we couldn't look at. And these are the ones we could see. And there are even more of those. You can mix redirects with pipes, too. The difference is the listing stops every time more stops the scrolling. So our list of errors is much shorter. All these permutations can and do appear in bash scripts. Pipes and redirects are very powerful. According to the Wikipedia article, pipes date to 1973 and were mostly implemented in one night, followed by days of programmers chaining programs together. So give it a try. Playing with these things is how you get comfortable with them, and it's how they were created in the first place. As you use Linux in terminal mode, at some point you'll notice that most command line programs take the same sets of wildcards, an asterisk to match all strings, a question mark to match one character, and so on. These are Unix tradition. Does the utility do any search and replace? Do you need to go beyond basic wildcards in your search? Is there a flag buried somewhere in the list that says use regular expressions? This is not an accident. This is regex, and regex is what this video is about. This isn't all of regex. Regex is old and it's powerful, and there's a lot of esoteric syntax. What I'm going to give you is the basics of regex. There is a cheat sheet you can download with everything I'm going to cover. There are far better cheat sheets out there that cover far more, but hopefully with this video, you'll have enough of the core functionality to use it and to understand the more detailed tomes on the project. So, what is regex? Regex stands for regular expressions. On the face of it, it's a simple beast that takes a pattern to look for in a larger body of data and outputs any line of that data that contains a match for the pattern. If you ask it, regex can replace part of the line before it outputs it. Regex isn't a standalone program or utility. It's a library you can build into other programs to give them this capability. One program that has regex built in is Nano. We just have to turn it on. For demonstration purposes, I've enabled regex processing in Nano. If you want to enable regex in Nano as well, here's how you do it. the first thing we have to find is Nano's configuration file. Nano is the configuration file for the Nano text editor. Nano reads this file every time it starts up. RC stands for Run Commands. Many Linux utilities still follow this convention with the letters RC in their configuration file names somewhere. As you can see, when we looked for the Nano RC file, we found it in the /etc directory. So I'm just going to edit that directly. And I do have to edit it from sudo or from root. This file is big. It has a lot of stuff in it, and most of it we don't need to mess with. So let's just use the quick search and replace function to find where regex is set up. That's Control-W. And here you see the line, set regex. This hash mark over here means that it's commented out. Nano will ignore this command when we start it. We'll take that comment out, and now the line is active. By default, Nano is also configured not to do case-sensitive searches, but case sensitivity is fundamental to Nano, so we need to turn that on too. So we search for the word case-sensitive, and here's another line, set case-sensitive, and we uncomment that too. Save the file, and we're done. If you prefer your text editor to use more traditional search and replace functionality, you can comment these two lines back out when we're done with the demos. Let's look at patterns. The simplest patterns are just like normal search functions. Type the text you're looking for. I have a text file here. It's got, well, gibberish in it, but it is useful because it gives us things to search for. So let's search for the word test. So we go Control \, type in test, and we're not going to replace it with anything. We're using replace because it will let us run the search over and over and over again. And there's the word test. And if we don't like that one, we can find another one and go back to the beginning. As you can see, Nano will repeat the search over and over again, irrespective of what's in regex. This is a character set. What the A to Z here means is that it will match any lowercase character from A to Z inclusive. It will match one lowercase character from A to Z inclusive. As you can see, it's matching only one character, meaning our word must be a three-letter word starting with a capital T, lowercase h. It will match the first three letters of any of these words, but the only whole word it's going to match is the. This is called a lazy match. It returns only the first character that matches the pattern. Well, we can change that behavior. The question mark is a quantifier that tells regex to do a different type of lazy search. It means match 0 or 1 occurrences. Since 0 occurrences of the pattern is still a valid match, you can see that it really actually matches everything in the file, one character at a time. It's also matching the blank spaces between words, even though they're not in the pattern, because 0 occurrences are still a match. If we replace the question mark with a plus sign, we can tell regex to match one or more occurrences of the pattern. You can see it's matching the lowercase letters in groups, but skipping the blank spaces since they're not characters from A to Z. And so on, and so forth. There's another greedy match quantifier, the asterisk. Asterisk matches 0 or 1 occurrences. Note how it's matching the blank spaces between words, too. We can mix the types of patterns we've talked about, and in fact, all the types of patterns that we will talk about can be mixed. Here I'm telling regex I want every word that begins with a capital T and has one or more lowercase letters after it. It matches this, and that, and the. I can also specify how many matches I want by putting it within these curly braces. Note how this pattern only matches the, but not this or that. It requires a capital T and exactly 2 lowercase letters. The /b is an anchor, which we'll cover next. It means the end of the word, or a word boundary. It means the word must end after 2 matches. If we leave the \b off, you can see that the pattern will match the first 3 letters of this and that, as well as the. Let's take a break, and when we come back in the next video, we'll continue with character sets. Welcome back. We're going to continue where we left off in the last video with character sets. You can specify multiple character sets in the pattern and multiple ranges of characters in a character set. They have radically different effects. This pattern matches any group of characters with 1 capital letter, here, 1 or more lowercase letters, here, to the word boundary, here. As you can see, it matches only the capitalized words in these lines. This pattern matches one or more capital or lowercase letters that occur before a word boundary. It will match every word and every character in every word. Character groups can also be negated. That is, you can make a pattern match anything not in the character group. The character to do that is a caret, and it must be inside the character group. Very important. This will match any lowercase character, space, punctuation, and so on, because we told it not any capital letter. As I said, the caret must be inside the character class. Putting it outside means something entirely different, as we'll discuss next. Anchors are special characters in regex that specify the position of the match. Caret matches the position before the first character in a line. $sign matches the position immediately after the end of the line. Here we'll try the caret. As you can see, it's matching the beginning of the lines. And we do the same thing with $sign. It will match the very end of the line every time. So if we want to match any uppercase T at the beginning of the line, we can do this. Caret, uppercase T. Likewise, we can search for any period at the end of a line. Period, $sign. And it hits every one. I mentioned \B earlier. It's also an anchor character, which means the word boundary. There are similar shorthands for commonly used character sets. Period is shorthand for any character except line breaks. Since that's dull to watch, let's make it greedy so it matches all the characters except line breaks. There are other shorthand characters, but they vary in implementation, and they don't work at all in Nano. Regex can provide processed versions of any match to a program. I've been using Nano's replace function rather than its search function, because replace has the option of repeating the search over and over again. You may have noticed I've been filling in the replace with field with garbage characters. With grouping, however, we can capture the matches of a given pattern and use changed versions of them in the replacement text. Consider this search. You've seen it before, but note the parentheses around it. That tells regex this is a group and that regex should capture the matches. If I fill the replace text with not/1, we'll replace each match, which will be a capitalized word, with the word not and then the original match. We'll just do them all. If we run the same replacement again, using the word seriously instead of not, so we can tell it apart, you can see that it matches both not and this, that, or the, each capitalized word. Since we have only one group, its matches will be returned in /1. If there were more, they would be in /2, /3, and so on. We've made kind of a mess of our test file, so let's clean it up. There are a number of ways we can do this, but let's imagine the file is 10,000 lines long, and not all the lines begin with seriously not. We want to search for 3 words in a row. If we replace all of this with just /4, should get the original file back. What we did was we told it to eat the first 3 words and replace the whole sequence with the 4th word. You can see it's matched exactly what we want. As I mentioned before, regex is a library in Linux. That means when you write a program, you need only include that library in your program, call it, and you can use regex within your program. It should be obvious by now that Nano has done exactly that. A great many other applications do as well. Regex comes in 2 general flavors, standard and extended. This matters when you call some utilities. We've been talking about extended regex. I've covered the backbone concepts of regex: literal patterns, character sets, grouping and capturing, anchors, and shorthand. Regex is big, it's rich. And while Linux regex is all one dialect, if you used to Perl or other programming languages, their regex can be a little different. There are lots of cheat sheets on the net, and O'Reilly has several books on the subject. This video is about the Grep and Sed command line tools. Most text editors, like Nano, have simple search and replace functions. Grep and Sed, at their simplest, are the command line equivalents of those functions. Let's talk about Grep. Grep is an extraordinarily useful tool for finding things inside a file. It stands for Global Regular Expression Print. Grep searches the input file or standard in for any lines containing a pattern. When it gets a match, the entire line is sent to standard out. Here you can see the output of ls. As usual, it's directories, files, and whatnot. But suppose we would like to find just the text files. We would go ls -r. For recursive, we want to dive all the directories, pipe grep.text. And you see that we have two. We have test.txt and test.text.save. Now we get to the regular expression part. The catch is, normal grep only takes standard regex, which is missing most of the shorthand, among other things, and it will fail silently by not matching anything if it doesn't understand the regex you throw at it. Another problem you can run into is that some regex characters have special meanings to bash. If your regex is even a little complicated, put it in single quotes so that bash leaves it alone. And we have a demo. Because this is standard regex, it works. However, a more complex pattern like this will not. Fortunately, there's egrep, or more properly, grep-e, and that's a capital E, today. This tells grep how to work with extended regex. With egrep, that same pattern that failed will now work. Grep can process large numbers of files if you give it a file name with a wildcard in it. There are a lot of flags you can pass to grep, only a few of which are meaningful at the command line. The rest are for writing command shell scripts, where, for example, having grep do nothing but return an error if there's no match is actually useful. These all affect the pattern. -e, and that's capital E, tells grep to use extended regex. -f, and that's a capital F, tells grep not to run regex on the pattern at all. Useful if you're searching a file for some regex. -v, lowercase v, inverts the match, so you tell grep to give you anything but the lines that match the pattern. And we have a demo. I've created a file called regex.txt, and you can see it has a regex expression in it. If I grep that file, -f, for a plus, you'll see that it actually does find it. It does no regex processing on the pattern at all. Let's take a short break. When we get back, we'll dig into grep's output flags. Welcome back. In the last video, we covered the basics of grep and its input flags. In this video, we'll cover grep's output flags. I've added some lines to test.txt. If I invert the search with the -v and the E for extended regex, you'll see that anything that matches this pattern is not returned, and everything else is. These next flags affect the output of grep independent of the pattern and any matches that may have occurred. -c counts the number of occurrences instead of outputting the lines. -l, and this lowercase l, returns the names of the files the pattern occurs in instead of the lines if you passed grep a wildcard instead of the file name. -n gives you a line number the match occurred in starting at 1. -r, and this lowercase r, tells grep to recurse into directories and attempt to match the pattern to all the files in that directory, just as ls-r does. I've created some duplicates of test.txt, test1.txt, and test2.txt. For this first demo, I'm going to count the number of occurrences of the word this in test.txt. And it says there are 3. And you can see that there are 1, 2, 3. This next demo will give me the file names of every file in my directory that matches the pattern test*.txt that the word this occurs in. And unsurprisingly, those are test, test2, and test1.txt. This next demo will give me the line numbers all the matches for the word this occurs in test.txt, in lines 1, 2, and 3. Let's take a break. When we get back, we'll dig into grep's counterpart, sed. Welcome back. In our last video, we worked our way through grep. In this one, we'll continue on with sed. Sed stands for Stream Editor. Where grep is the command line equivalent of search, sed is the command line equivalent of replace, albeit with a command-driven editor wrapped around it. Like grep, sed is an old, extremely powerful tool for throwing large numbers of files or very large files at. Sed, like grep, is a line-oriented filter. A file is passed to it, and it searches for its pattern, line by line, does something to the line based on the command and/or substitution text, then outputs or writes the result, depending on the flags that are set. The basic sed call contains 2 parts, the option or command part, and the input file, or standard in. The most common form of sed is a substitution. The command for this form is s/search pattern/substitution text. In this demo, we're going to replace all the word this in test.txt to that. That was easy. Sed can run amok with simple searches and replaces, just like any other search and replace. If we wanted to output test.txt with all past tense verbs, we might try this pattern. But that doesn't do what we want, for a couple of reasons. Sed uses basic regex by default. This means that our pattern is matched once per line. So when Sed hits the is in this, it matches that and changes it to was, and then, in a lazy match, ignores the rest of the line, which gives us that mess there. If you know regex, you know there are a couple of ways to fix this, but we have to give Sed the -r flag to use extended regex. \b stands for word boundary in regex. This means that the word is must be all by itself. Now it works. Sed has a reputation of being hard to use. It's not terribly, but a combination of sed // quoted regex, and some flags makes it look like line noise. The most used command in sed is s, as you've already seen. This stands for substitution, and is most like the search and replace functions in editors such as Nano. There are other commands, such as c, which substitutes the entire matched line with the replacement text, and a for append, which appends the replacement text to the end of the line containing the pattern. Their syntax is a little different. What I've told Sed to do is to match any line with the word is in it and append the words found and is to the end of the line. What I've told Sed to do here is essentially the same thing. Find any line with the word is in it and replace it with the words found and is in test.txt. The Y command tells Sed to transform text. What I've told Sed to do is anytime it finds the letters lowercase I or G, replace them with uppercase versions. And you can see that it has. Sed is mostly a wrapper for regex and extended regex. The pattern can be any valid regex pattern, including grouping and capturing. The substitution text can also be any valid regex substitution, including \1, \2, and so on to access captured groups. You can pipe the command to some other function or redirect it to a file with ease. This is ugly, but it's not that difficult. We're calling sed, we're telling it to use extended regex, we are doing a search and replace, we are searching for any capitalized word that ends on a word boundary, replacing it with the word captured and the captured group itself, which is that original word. We are operating against the file test.txt, and we are redirecting the output to captured.txt. As you can see, it prepended the word captured to each line, but because these do not begin with a capitalized word, they were left alone. As with most Linux command line utilities, sed takes a plethora of flags. Many of the flags only apply to certain commands and have special locations they have to be in for that command. As an example, we'll look at the I flag for substitutions, which tells sed to ignore case. The space is critical. It separates the command and the search and replace pattern from the file name. Note how my search pattern does not contain a capital T in this, which is why we don't match anything and no substitutions are made. If I add the I flag to the end, like so, sed becomes case insensitive and does what we expect. You can see that all the this words have been replaced with a lowercase that, whereas existing that's and thes and whatnot were not touched. More normal command line options are -r, which turns on extended regex, and -n, which suppresses printing by default. You then specify a /p at the end of the substitution group to print only when a match is found. This makes sed function more like grep. What I've told sed to do is do not always print. Substitute the word that with the word this, and only print the lines which you have done the substitution in. This video is about the Whereis utility, path names, and search paths. Up until now, we've been living under the assumption that cd, pwd, ls, grep, and whatnot are all parts of bash. The truth is, other than cd, most commands aren't. They're really file names. When bash encounters a command it doesn't know, it searches a specific list of files for a file by that name. If it finds one, It executes it, and we don't notice the difference. This also means that should you use a different command shell, most of your commands will actually be the same. Whereis tells you exactly where those commands live. This is the ls program, called an executable, and this is its man page, or the file that tells you how to use it. You don't have to know the second one. pwd is the same way. Bash itself is the same way. For that matter, so is whereis, but it's not in the same directory. Why aren't all these programs in the same place? The answer is that once upon a time, volumes were small. The first hard disk I ever owned was 40 megabytes. For that drive to hold an entire Linux installation, even in the early 90s, would have left no usable space on the volume if it fit at all. But if that volume contained /bin, /boot, and /dev, and a few other critical directories, the system would be able to boot, and then mount other volumes into its directory tree. Perhaps they might contain user bin and home. The system could then go on its merry way until it was ready for users to log in. So how does Bash know where to look for these commands, especially if you add one that wasn't there before? The answer is that Bash has search paths, which are lists of specific paths where Bash looks for commands. They can get quite complex. They're stored in a Bash environment variable. You can see the path your copy of Bash is searching like this. Note that path must be uppercase. Echo is a Bash command that tells it we want to see the contents of a variable. $sign tells Bash that this next bit of text is a variable name, and path is the variable name. That's a list of directories separated by colons that Bash searches every time a command is typed that it doesn't already know. It's set in your Bash startup file, in this case, on this particular Ubuntu virtual machine in .profile. There. It looks a little strange. Path equals $home. That is another environment variable. In this case, it translates to /home/jrs/bin, which is a directory inside /home/jrs, and then it appends the entire existing path. Your search path may also be set in .bashrc, .login, or any of a number of permutations. You'll have to look up your Bash startup files for your specific Linux distribution and make sure to remember that you want the non-login version if there is one. Putting a path in the wrong one is very frustrating because it doesn't work. You should also know that if you're writing command shell scripts, you don't know what the path environment will be set to, if anything. Always call external programs in scripts by their full path names. Power Boost Unlocked, Sudo and Su. This video is about Sudo and Su, two ways to get superuser or root, as it's more commonly called, privileges. Everything in Linux is a file. This is the security model because every file has in its inode table entry a list of permissions, owner, group, and world. If the permissions don't allow you to access a file, even if you own it, Linux won't let you access it. It's mostly that simple. But what if you do need to access it? What about files owned by the system? What about all that? That's where root privileges or superuser privileges come in. The traditional Unix security model is simple. You're either root or you're not. And if you're root, file permissions do not apply to you. Can root make a huge mess of the directory tree? Absolutely. Root can wipe the whole system with a single rm command. Though this is somewhat harder now than it used to be. RM has safety rails and warning signs now. Does every running program or process started by root inherit root's superuser privileges? Yes, it does, unless you tell it otherwise or the program is coded that way. If an outside attacker were to log into the root account, they could take over the system. It's that simple. Because of this, there are two basic approaches to keeping root secure. Sudo, with a disabled root account, and Su, with an enabled root account and a very, very good password. If you don't recall setting a password when the system was installed, try your own. The sudo approach to securing the root account is to set it up so that nobody can log into it. Then create a program that runs with root privileges, which gets deeper into file permissions than we've gone thus far, and has a list of those who may call it. That program is sudo. It's used in Debian-derived distributions like Ubuntu and Raspbian. Note how I'm not even allowed to look in the /root directory. Sudo asks me for a password, my own in this case, and then executes my command with root privileges. Sudo is essentially another command shell, albeit one that lets you execute one command per run. Every time it's used, it will log by whom, and it can be configured to log what commands were used. Here's the log file that sudo generates. Note that your sudo log may be called something else in different distributions. Sudo can also be configured to allow only certain commands, though typically with the root account is disabled, this is not done. If you need to enter multiple commands with superuser privileges, i.e. run them from root, this can get tedious, and sometimes it doesn't work at all. The easiest way to get around this is to call bash from sudo. Note that sudo does not ask me for my sudo password after the first time. Because sudo gives root or superuser privileges to every command it runs, if it lets you run bash, the bash process will also have superuser privileges. Bash is telling us that, with the change of the username and the change of the prompt. Su, or Su, is a command. It stands for switch user. It lets you log in as a different user without logging out of your account. It will ask you for the password of that account and log you right in, as though you came in from the outside. Here, I'll Su to myself. When you don't give Su a username, it defaults to the root account. Because we're now on a Fedora virtual machine, and because Fedora does not disable root, we can log right in. The password is set when you install Linux. Fedora's philosophy is that it's better to have a root account enabled. Once you log in as root, you are looking at a bash shell with superuser privileges. Linux will do what you tell it, even if you tell it to do something self-destructive. Linux, like most Unix-like operating systems, comes with a manual. This is invoked with the man command. You may occasionally still see references online to RTFM, which stands for Read the Fine Manual. Some old-time Unix people might dispute the adjective. Man pages cover nearly every Linux command and utility. These are written by software engineers for other software engineers, and not necessarily anyone else. They're usually thorough, but the style can be terse. Some of them are quite ancient as well, dating back to at least the 1980s. But in Linux, there's an active program of maintaining the man pages, so most of them will be fairly recent. Typically, a man page is broken into several sections. Up here, you have the name and a quick description of what the command does. We're looking at grep, as you can see from the header. Here, labeled synopsis, you have the command and how to pass parameters to it. These, like many things in Linux, can look like line noise, but they're giving very specific information. Square brackets tell you that a given parameter is optional. So in man grep, we can see that it takes an optional option, or flag as we've been calling them, there, requires a pattern, there, and takes an optional file. Otherwise, it defaults to standard in. On the second line of the synopsis, we can see that there's an alternate way to use it. It takes optional options, and optional -e for extended regex, and a pattern. And that pipe character, the vertical line, is a logical OR, which means in this context that if you don't want to give it -e and some regex pattern, you can give it -f and cause it to read a file for its pattern. Then it takes an optional file to compare the pattern. Next is a detailed description of what the utility does. It lists any variants. In this case, 3 separate variants of grep have been merged into one program with 3 different flags. If you look at /user/bin/egrep, you'll see it's now a bash script that calls grep -e. Next come the options or flags. Depending on the utility, there may be additional sections after the flags, like grep has when it discusses regular expressions at some length, environment variables that affect grep, exit status, which you can pick up if you're using grep in a bash script, known bugs, and notes. The man pages are broken up into sections, 1 for executable programs, shell commands, and basically user stuff, 8 for system administration, usually only for root. 9 may have kernel routines, but this isn't standard. A man page will tell you what section it came from. If you don't specify which section you want, it defaults to the lowest available. This is the man page for regex. As you can see, it's a library call, so it is level 3. Your topic may be covered in multiple sections. The -a flag will give you all the man pages that match your search. Here it is as a library call and programmer's manual, section 7. I want to read the page from section 2, which is system calls. Section levels are covered in man. Here. If you don't understand a command, man is a good first place to look. If you don't understand the man page, do a web search and you'll often find it has much more readable language with examples. The directory tree is a lie. We're told that everything on it is a file and that everything mounted to a directory tree is a volume, which is really a disk somewhere. That was true once upon a time. Things are different now. This video is about all the stuff our directory tree is really made of. Here's the story you've been told. This is the directory tree. It starts at root, it branches down through every subdirectory to every file known to the system. Everything in Linux is a file, and every file lives on the directory tree. The truth is, you already knew the directory tree is a bit of a deception. Some of those directories are really other file systems. Most of the time, the user or users won't notice. Users definitely will notice if that particular file system runs out of space, so it's important as a system administrator to keep in mind what's mounted where and how big it is. Let's start there. DF stands for Display File System. If you believe the man page, all it tells you is how much space is left in each file system mounted to the directory tree. It does that, but it's implicitly telling you a lot more. I'm sending DF the -H flag to tell it I want human-readable file system sizes instead of some obscenely long number of 1K blocks. This is a real file system. You can tell because it begins with a device driver /dev/sda and ends in a number, 1. The number after the device driver tells you that there is more than one partition in that volume. I'm sending DF the -H flag to tell it I want human-readable file system sizes instead of some obscenely long number of 1K blocks. This is a real file system. You can tell because it begins with a device driver, which is in /dev, in this case, /dev/sda. The number tells us that this is a partition, or part of a volume, and that other partitions could be mounted which would share the device driver. We'll cover partitions in another video. Here's how big this file system is, 13 gigabytes. Here's how much of it is used, 5 gigabytes. How much of it's available, 6.7 gigabytes. The percentage of use, 43%. And most importantly, where on the directory tree it's mounted. In this case, it's mounted at root. Virtual file systems are some of those things you find in the directory tree that aren't quite what they seem. A virtual file system is a running program or a process that offers storage optimized for specific purposes, which is accessed through the file system mechanisms. It all looks pretty normal, but notice these file systems don't have a device driver associated with them. Tempfs does, but it's not in /dev where it belongs. Tempfs, or /run where it's mounted, is a program pretending to be disk space. Like all running programs, it can be swapped out to the swap partition. Likewise, the runlock, runshm, and runuser partitions are a program or programs storing data for Linux itself and for other programs. Linux uses a lot of temporary files to hold things like the state of a running program, lock files, which guarantee exclusive access to some other file by listing that file and who has exclusive access to it, the actual messages of interprocess communications, and so on. None of these files need to be preserved between reboots, and the faster these files can be accessed, the faster the system can run. UDEV is another virtual file system. It gives Linux and Linux user programs a convenient interface to access and secure device drivers, which are really part of Linux itself. As you can see from this df-h display, when we cd to /dev, we're really looking at this running program pretending to be a file system, giving us handles for each device driver. Linux uses a lot of temporary files to hold things like the state of a running program, lock files, which guarantee exclusive access to some other file by listing that file and who has exclusive access to it, the actual messages of interprocess communications, and so on. None of these files need to be preserved between reboots, and the faster these files can be accessed, the faster the system can run. A lot of people get twitchy when they see a virtual file system like UDEV with 2 gigabytes of space available. It seems like a lot of memory, but that's a maximum figure. Used is how much memory they're really taking up. More importantly, because these are running programs or processes, if they're not being used right now, or part of the data is not being used right now, they can be swapped out to the swap partition, which is a real file system on a real volume, to free that memory up. Let's take a short break. When we come back, we'll get into how to mount and unmount file systems. Welcome back. In the last video, we left off with the discussion of virtual file systems. In this one, we'll dig into mounting and unmounting file systems by hand and auto-mount. The other lie the directory tree tells us is that when you plug a device into USB or a similar connector, it just appears as if by magic. Once in a while, you'll run into one that Linux doesn't know how to mount, and it will be up to you. Here's how it's done. I'm using my USB floppy drive for this demo. You might hear it in the background. I've just inserted a floppy, but you can see the floppy hasn't shown up. It has not been mounted to the directory tree. USB floppy drives do not offer a file system until a floppy is inserted. By this time, however, AutoMount has given up. So we can either unplug the floppy drive every time we change floppies, or we can mount it ourselves. The first thing we'll need is a mount point. That is, a directory where the new file system can be connected. Remember, nothing in this directory will be visible after the mount, so it's best to leave it empty. Next, I need to know what the floppy drive's device name is and what kind of file system is on it. We'll use the fdisk utility for that and pass the -l, lowercase l, flag. fdisk is a very powerful utility for manipulating file systems and partitions. It has few, if any, safety features. We'll cover it in another video at some length, but for now, please be careful with it. Okay, we know that the floppy drive's device driver is /dev/sdb because it says so right here. You may know that the DOS file system is often called FAT, for File Allocation Table, and that the most modern and commonly used flavor as of 1995 is called VFAT. If you didn't know that, you can look it up on the web. Does our Linux machine support VFAT? Let's see. All the file systems the Linux system knows about will be stored in /proc/filesystems. There are a lot of them, but let's look for only the ones we're looking for. There it is. Now we have all the information we need to mount the floppy. We have a mount point, we know what file system is on it, and we know that the system supports that file system. So let's mount it. What we're telling it is mount -t for file type, VFAT, the name of the device driver, /dev/sdb, and the mount point we want it mounted to, /media/jrs/floppy. And there it is, on the device driver, /dev/sdb, mounted exactly where we told it. Let's check it out. Yep, there's a file. Before you eject or unplug any volume from Linux, you must unmount it so the system knows to let go. Umount doesn't need as much information as mount does. All it needs is the device driver. Target is busy? Well, that error means that something is reading the file system. There are ways to override it, but in this case it's easy to see what running program is accessing the floppy. We are. Look at the bash prompt. We're still in the floppy's directory, and it won't unmount as long as we are. Now it unmounts without protest. AutoMount is a function of the UDEV system. Remember UDEV? It's one of our virtual file systems, and that's where all the device drivers live. UDEV is a daemon. That means it is a program which is started at boot time and runs in the background to provide a service to Linux. The service it provides is that it watches for Linux events, such as when a USB device is plugged in, or when a terminal is switched on. Remember that /dev is in the UDEV virtual file system, and that device drivers are really files like anything else. The catch is, UDEV creates those files on the fly for a given event. I've unplugged the floppy drive from the virtual machine. When I plug the USB floppy drive back in, fdisk-l still doesn't show anything because there's no floppy in it. But if you look in /dev, you can see that the /dev/sdb device now exists. Linux knows the floppy drive is there. If this were a USB flash key, the file system would already be connected, and AutoMount would have already mounted it if possible. UDEV's behavior in all of this is controlled by rules. If you have some device that's not being connected right, or you want the permissions set differently when the device auto-mounts, you can modify the UDEV rules. They're in different places on different distributions, and you want to be cautious about modifying them, but now you know they're there. The Linux directory tree is a lie, kind of. Really, it's an abstraction. Linux treats everything as a file. Once upon a time, the things you see in virtual file systems like UDEV were real files on a volume. The UDEV daemon and its counterparts offer these services that look like files, and as a result, we can still secure them with the same mechanisms, still access them with the same mechanisms, no matter what is going on behind the curtain. One of Unix-like operating systems' greatest strengths is this model, because it lets you change what's going on behind the curtain. So long as it looks the same from the directory tree, even ancient applications like Xterm will still run as though nothing's changed. In times of old, when floppies were king, they had but one file system each. If you wanted a different file system, you got another floppy and you formatted it. And then came hard disks, and they got bigger fast. It didn't take long before hard disks got bigger than some file systems needed to be, and people wanted to put more than one file system on a given hard disk. Thus, partitioning was born. So, what is a partition? A partition is a way of allocating an area of a larger volume to act like a separate file system. To stretch my analogy a little further, it's like having a whole box of floppies on one volume. Logically, they're as separate as if they were separate volumes. They must be mounted and unmounted separately, formatted separately, and so on. The good news is, if you wreck the file system on one, the rest of the partitions on the volume shouldn't be affected. You can put different operating systems in different partitions, and put your user's data on its own partition if you want to. They're useful things, and we're going to cover how they work and how to create and delete them in this video. By the way, if you've never actually used a floppy, they're like flash keys fresh out of the package, except they don't hold as much. A brief rant on units. Up until now, I've been suggesting that using kibibytes instead of kilobytes and so forth is pedantic at best. Quite frankly, that's still my attitude. But it's like trying to sweep back the tide, so here's the difference. The prefix kilo, when used in decimal notation, is 10 to the third, or 1,000. The prefix mega in decimal is 10 to the sixth, or a million. The prefix giga in decimal is 10 to the ninth, or a billion. That's a short-scale American billion. The largely defunct, long-scale British billion was 10 to the 12th, what Americans would call a trillion. The JEDEC, or Joint Electron Devices Engineering Council, standard, asserts that these prefixes have different meanings in binary, and they established the standards for RAM, so their opinion carries some weight. Under JEDEC units, a kilobyte is 2 to the 10th, or 1024. A megabyte is 2 to the 20th, or 1,048,576. A gigabyte was 2 to the 30th, and you can see how much it equals here on the slide. RAM is measured in these units. A gigabyte of RAM is 2 to the 30th bytes of RAM. It would make sense to measure drive storage in the same unit, wouldn't it? Not if you're a hard drive maker. When gigabyte drives first began to hit the market, hard drive makers discovered that using decimal-based gigas, that is 10 to the 9th bytes, meant that hard drive makers could sell a 953 MB drive as a 1 gigabyte drive, even though it wasn't. This is called marketing. When challenged in court, drive manufacturers argued that the international standard for a giga is a decimal giga, 10 to the 9th, and they ultimately settled by paying off users and putting weasel text in the specs. And now, I guess, we're used to it. In response, a new standard, IEC 80,000-13:2008, was drafted and approved that specified new prefixes that are strictly binary. They even have by in each one to make it obvious. Kibibyte, for 2 to the 10th bytes, is abbreviated kib. Mebibyte, for 2 to the 20th bytes, is abbreviated mib. Gibibyte, for 2 to the 30th bytes, is abbreviated gib, and so on. I mention this because Parted, our partition table tool, defaults to using hard drive maker weasel units until we tell it not to. I use the SI standard grudgingly at best, and I'll probably revert to the JEDEC standard when we're not dealing with disk size. In order for different parts of the volume to be reserved for different file systems, something, somewhere, needs to keep track of what's where. A partition table lives in a special area of a volume. It's a lot like a directory table, except that your computer, even before it's booted, knows what to do with it, and it is file system and operating system agnostic. This is the partition table of this virtual Linux box. You can see it's got one volume, /dev/SDA, and 3 partitions. The boot partition, here, an extended partition, here, and inside the extended partition is the swap partition, here. If we look at df-h, we can see that /dev/SDA1 is mounted at root, and in the case of this virtual machine, it contains the entire visible file system. /dev/SDA5 is the swap partition. We'll cover those in another video as they're a topic unto themselves. Your partition table may be quite different. Here's the partition table of my Fedora virtual machine. The traditional partition table for PCs is the MBR for master boot record, or DOS partition table. The master boot record, also known as the boot sector, is at the very beginning of the volume in sector 0. It contains the bootstrap code, which tells the BIOS of your computer, I'm a volume, and I will be feeding you your operating system today. It also contains a simple partition table, so it can inform the BIOS and the operating system what's where. At address 0, and these are hexadecimal addresses, you have the bootstrap code. At 1B8, we have a disk signature. 1BC, we have some copy protection, which, as far as I can tell, is never used. 1BE to 1EE are the 4 partitions you are allowed, and they take 16 bytes each. And 1FE and 1FF are boot signatures. What I've done is told hexdump to give me the usual mixed hexadecimal and text display, and to give me the first 1024 bytes, 2 sectors, of /dev/SDA. Because it's a virtual machine, this machine still has a DOS-style partition table in its master boot record in the first sector. Here's the boot code. All of this, including this error message. There's some drive signatures and some stuff. And this here, at 0x1BE, is the first partition. The hexadecimal 80 here indicates that this is a bootable partition. We have a start address here. The 83 here indicates that this partition holds a Linux file system. Ending address here, logical block address of the first block here, number of sectors in the partition here. There's a pretty good chance that if you try this on your own Linux machine, you'll get something more like this. This is a UEFI header, and we are not in Kansas anymore. Let's take a short break. When we get back, we'll take a quick look into the GUID partition table. Welcome back. In our last video, we talked about the master boot record or DOS partition table. It's still around, but more and more Linux systems use and boot from the GUID partition table, in no small part because they have UEFI BIOSes. If I sound like the text on a motherboard box, bear with me. I'll explain. UEFI is the modern replacement system for BIOS. It stands for Unified Extensible Firmware Interface. Most real PCs, as opposed to virtual machines like mine, and all modern Macs will use UEFI instead of BIOS if they were made in the last 10 years or so. These will use the GUID partition table, or GPT, instead of the master boot record. GUID stands for Globally Unique Identifiers. There are a lot of differences between the GUID partition table, or GPT, and the MBR partition table, even though they do essentially the same job. The most notable for us is that it can handle volumes larger than 2 terabytes. MBR can't. The GUID partition table was designed to coexist in the MBR world, so it contains a simple MBR partition table in the first sector of the volume. This table contains one volume of this type 0xEE that spans either the full volume or the first 2 terabytes, so that tools that don't know about GUID won't mess the volume up. We can wade through the GUID partition table the same way we did with the MBR one, but it's big. Partition table entries are 128 bytes each, and there can be 128 of them. Also, the partition table is duplicated at the bottom of the disk. GUID was meant from the get-go to be handled by software. The tool for the job, in the terminal environment at least, is parted, and you'll need root privileges. I've passed parted the -L flag to tell it to list all connected block devices, that is, all volumes, whether they're mounted or not. You've seen this before. Here's /dev/SDA, here are the 3 partitions in it. Here's a flash key I just plugged in. It has one partition called test, and is a GPT partition table. And in fact, it's the one we were just looking at. And if we do a df-h, here are those same partitions. SDA1, mounted at root, has everything on it. These, as you know, are virtual services. And here is /dev/SDB1, which is the flash key. The swap partition doesn't show up in df-h because the swap file is not and must not be mounted. It's used by the Linux system to extend its memory by using disk space. We'll cover that at length in another video. Let's build some partitions. First thing we'll need to do is unmount /dev/SDB1, the flash key. And then we start parted. Stop there. This is how mistakes happen. Did you see that I didn't tell parted what volume to use? See here, where it tells me that it's using /dev/SDA. That's my boot volume. Because this is easy to do, it's always a good idea to hit P to show the existing partition table before you change anything. Make sure you're looking at the volume you think you're looking at. Let's point this at the flash key where it belongs. Okay, that's what I expect to see. Parted has a list of commands. Before we go further, I should point out that parted uses Weasel megabytes by default. In order to get sensible values out of it, we need to tell it to use megabytes. Before pressing return, I should point out that this is another one of those places you can do something you'll truly regret with one keystroke and no warning. If the data in that partition has any value, think twice before pressing return. So now we have empty space where one partition was. But let's go further. Let's start a whole new partition table. Let's make it an MBR table. I know, I called it an MBR table, and that's its proper name, but that's not what Parted calls it. Parted calls it an MS-DOS partition table. For once, Parted gives us a warning. And now we hit P to see our new table. Unsurprisingly, it's empty. If we want to create a GUID partition table, it's the same process. Let's take a short break. When we get back, we'll make some partitions, both the GUID way and the MBR way. Welcome back. In the last video, we covered what the partition table is and how to make and destroy them with Parted. In this video, we'll make partitions of various types, both the GUID way and the MBR way, and we'll build some file systems on them, mount them up, and mess with them. You already know what a partition is. It's an area of a volume allocated in the partition table, which behaves like a separate disk with its own file system. So, enough talk. In the last video, we created a GUID partition table, or GPT, on this flash key. Let's create some partitions in it. Nothing in the partition table. The entire space is free. But since Parted insists on using Weasel megabytes and gigabytes, let's force it to use the IEC standard. The first thing it wants is a name. The square brackets mean exactly what they do in man pages, but this is optional. I'll call it test1. Let's make this file system a VFAT, or FAT32 partition. Parted calls VFAT file systems FAT32. They refer to the same thing. The difference is which device driver is installed on your particular Linux computer, because the drivers have somewhat different capabilities. Where do we want this partition to start? Well, there are considerations. For a flash key like this, it's much more important to use all of the space available than to get every last bit of performance out of it. Let's face it, flash keys are slow regardless. We can put in 0 and Parted will sort it out. But if we were putting this volume into a RAID or some other complex volume setup, alignment on 1 MIB boundaries matters, and it can make a huge difference in performance. And on modern terabyte volumes, we can spare most of a MIB for performance. If you grew up with floppies that held a fraction of a MIB like I did, try not to let this irritate you too much. Storage is cheap. We'll go ahead and align it to the MB boundary. Let's make this a 1 GB partition. With Parted, we can just tell it that. But isn't a gigabyte 1024 MIBs? Yes, but we are specifying the endpoint and not a size, so we have to add 1 MIB for the one we threw away at the beginning. In some cases, your partition may automatically mount. Parted knows about some file systems and has plugins for more. It may know FAT32 and may automatically format that partition for us, and AutoMount will pick it up and do what it's supposed to. If we hit P, we can see that we've created a partition. Print free shows us we have another 902 MIBs free. Let's make another. You might have guessed we can put all the parameters in one line, so let's do that. Here, it's complaining that in fact our free space doesn't start at exactly 1025 MIBs. Important safety tip: Parted rounds to the nearest unit. If we accept this, Parted will warn us that we're not starting on the MIB boundary. That's not acceptable for this demonstration, so we'll say no, and go back and waste another MIB. If we print free now, we can see that we've allocated almost all the space on this device, except for almost 3 MIBs, so we could hit our MIB boundaries. Repeat after me. Storage space is cheap. So why didn't our partitions mount automatically? If your partitions didn't mount automatically, it means that your installation of Parted doesn't know about ext4 partitions by default, so it didn't format or make the file system on it. We have to do that by hand. Parted-L shows us the volume we want is on /dev/sdb2. The command we're going to use in this case is mkfs.ext4, or make file system ext4. If we had an ext3 file system, it would be mkfs.ext3, and so on. A FAT32 file system is different, using the mkdosfs file system creator. They all work pretty much the same. It does require super user privileges. And it's done. Let's do it again. Makefilesystem.ext4 has some very basic safety rails. If it finds a valid file system on the volume, it will ask you if you really want to do this. But each of these file system utilities comes from a different group of writers, so don't rely on this. Check before you hit return. So let's not do it again after all. MKFS does not trigger auto mount, so let's mount it by hand. And if we do a quick ls on /media/jrs/flash2, we can see the lost and found, which is in every file system except MS-DOS, or FAT32, or VFAT. They're all the same. If we're working with an MS-DOS or MBR partition table, making partitions is pretty much the same, but there are a couple more things you should know. There are 3 general types of partitions in MBR partition tables, as opposed to just one in a GUID table. Primary partitions are just like the ones in GUID partition tables. You make a partition, you put a file system on it, you mount it, end of story. You can have a maximum of 4 of them. Extended partitions are weirdos. They were added later when people found they needed more than 4 partitions as drives got larger. You can have only one extended partition, but it holds logical partitions. Logical partitions are contained in an extended partition, but they are otherwise pretty much the same as a primary partition and a GUID partition. How many of them you can have varies among operating systems and drive technologies, but 15 total partitions seems to be a safe limit. So let's make some partitions. Switch to MIBs, so parted is sensible. Print free to show how much space we have, and make a partition. The first thing makepart wants to know is the partition type. Let's make it a primary. Then the file system type. Let's go with FAT32. Let's not worry about 1 MIB boundaries on this one. Start at 0 and let parted fix it for us. Again, parted is rounding for us. This is fine. Parted is also warning us about alignment. This time, we don't care. Hit capital I for ignore, because lowercase I will be ignored. Print free to see what we have left. So we have 903 MIBs free. Let's chop that into a bunch of logical drives. We've now made the extended partition. Now if we type print free, we can see we have 2 partitions eating up the whole volume, but we still have 903 MIBs free. That's because our extended partition is empty. Let's make some logical partitions. This one's tiny, less than a MIB across. Note that it's partition 5. Remember that partitions 1 through 4 can be primary or extended partitions. Logical partitions begin at 5 regardless of whether all 4 primaries are in place. And there we go. Once the partition table is set up, the partitions handle exactly the same for formatting and mounting. Logical Volume Management, or LVM. To review for just a moment, partitions provide an abstraction between file systems and physical volumes. This abstraction allows you to subdivide a large physical volume into multiple file systems. There's no free lunch. It takes more memory and processor time to operate this abstraction, but those resources get cheaper every day. Logical volume management does something closely related. It substitutes an abstraction in place of physical volumes. This abstraction allows you to merge multiple partitions into one logical volume, even if those partitions are on different physical volumes. It gives you many new storage management capabilities in exchange for more memory and more processor time, both of which get cheaper every day. In order to understand logical volume management, you have to understand 3 basic concepts. Physical volumes, or PVs, are partitions or drives. If you understand partitioning and partition tables, you already know most of what you need for this. Volume groups, or VGs, are, as the name suggests, groups of physical volumes pooled together. You'll need to know how to make them and maintain them. Logical volumes, or LVs, are created out of that pool of space. You'll need to know how to create and maintain these, but once you know they exist, they handle almost exactly like partitions. You make a file system the same way, you mount them the same way, and so on. You could, in theory, partition them, but this kind of defeats the purpose. I've installed the LVM2 software package on this virtual Ubuntu machine. You should be able to find it for your Linux installation with a web search. Make parted units make sense? I'm making a GUID partition table. MBR tables will also work. Here's where we diverge from the normal partitioning process. We need to set a flag on this partition so that LVM knows it can talk to it, and so that if we ever look at this volume and part it again, we realize it's an LVM volume. Set the flag, 1 for partition 1, LVM for the flag we want to set, and on for the state we want. The next step is akin to formatting the partition we've created on a volume, but it sets it up for LVM use instead. In LVM, PV always stands for physical volume. That means we're doing something to the actual physical volume or partitions on it. So PV create creates the PEs, or physical extents, on the physical volume. And we're done. Our new physical volume is ready to go. I've prepped two other flash keys to be LVM volumes exactly the way I just showed you. The next thing we need to do is make them a volume group and pool their physical extents, or PEs. All volume group commands begin with VG, so sudo VG create. VG0 is the name of the group, and there is nothing special about that name, /dev/sdb1/dev/sdc1. You can create a volume group with as many or as few volumes as you like. Let's start with 2. Now we can display what we've got with the VG display command. This tells us everything we need to know about VG0. Its name, what format it's in, LVM2 in this case. There is one metadata area per physical volume, so we have 2 in this case. We can read or write to it. It is resizable. It has 2 current and active physical volumes, and its total size is 17.07 gibs. PE size roughly corresponds to sector size in a physical volume. By default, they're 4 MIBs. If you know this group is going to be storing images of at least a gib each, you can change the physical extent size, but 4 MIBs is fine for now. There are 4,371 of them, which, if you multiply it up, gives you right about 16 gibs, which is about right. You lose some for metadata and so on. But what if our needs change, and we need more extents than this in our group? What about that third flash key we just prepared? Just add it in. VG extend, group name VG0, /dev/sdd1, which is the new drive. Now you can see we have 3 current physical volumes, 3 active physical volumes, and we have 17.54 gibs of space in 4489 PEs. Maybe we should take one of the PVs back out. Note that if a logical volume is using this, you have to do some prep first, which I'll cover shortly. But to get the volume back out of the group, we just do this. What's really handy is that you can do this while there are logical volumes using this group, and while those logical volumes are mounted and running. Let's take a short break. When we come back, we'll build some logical volumes, and I'll show you some of the really handy things you can do to them. Welcome back. In the last video, we introduced logical volume management, physical volumes, and how to group them into volume groups. In this video, we'll talk about logical volumes and some of the handy things you can do to them. We have a volume group with all those PEs ready. Right now, it doesn't do us much good. Let's make a logical volume. Any LVM commands dealing with logical volumes begin with, you guessed it, LV. That's LV create, specify the name in bytes instead of extents. If we used lowercase l, we could specify it in physical extents. 1 gib for the size. Group name is VG0. Volume name by name is LV0. Again, this name has no particular importance. You can see our VG display has changed. We have a current logical volume. We've allocated 256 PEs for a total of 1 gib. And we have 4,115 gibs free. We have a new command we can look at the volume with. Unsurprisingly, it's LV display. If we don't tell it what logical volume to look for, it will give us all of them. We have one called /dev/vg0/lv0. If we wanted to see that one specifically, we could go sudo lv display dev/vg0/lv0. We can also see it with parted, although it gives us a much less convenient device name for it. And that's it there. Parted's complaining that there is no file system on this volume yet. And it's right, so let's fix that. File system selection does matter in logical volumes. Some file systems can't be resized easily. ext4 can expand on the fly and can be reduced when it's unmounted, so let's use that. And done. Let's mount it. You do this like any other volume. ls/media/jrs/mount point works. There's the lost and found, which is normal for any file system, and we can make some files on it. All pretty much normal. Here it is in df-h. There's that inconvenient device name I was talking about. Let's have some fun. Let's say we want LV0 bigger. First, let's give the logical volume some more space. The command to do that is lv extend. We want to extend /dev/vg0/lv0, a size in bytes instead of extents, and add 1 gib. Note that not only did I not dismount the logical volume, but that the file system size hasn't changed. We resize the file system with the resize to fs command. If we don't specify a size, it will make it as big as the volume it's on. Note that I still haven't dismounted the volume. And there it is, now 2 gigs wide. And our test file still works. We can shrink the logical volume too, but it's a little more complicated. We have to do it in exactly the reverse order. Shrink the file system, then shrink the volume, or we'll wreck the file system. It's also a good idea to have a backup of this file system before you shrink it. If you make it just a bit too small, you can lose files or file system integrity. The first thing we must do is unmount the file system. Next, we need to do a file system check on it. Always do fscks on unmounted file systems. The -f flag forces checking of the file system, even if it doesn't seem to need it. Resize to fs will tell you all of this and refuse to do anything if you haven't already checked the file system. No problems. Note that resize to fs uses real JEDEC gigabytes, megabytes, and kilobytes, and has a huge rant on the subject in the man page. df minus lowercase h, by the way, also returns JEDEC megabytes, gigabytes, and kilobytes. Only use uppercase H if you want weasel units. You can see our file system is smaller again. But the logical volume isn't. We can fix that with lv reduce. As usual, lv reduce, device name, -l for bytes, and -1 gib. Remount the file system. Files are still there. And they still work. Let's take another short break. When we come back, I'll show you how to move a logical volume from one PV to another. Welcome back. In the last video, we talked about making logical volumes and resizing them. In this one, I'll show you how to move a logical volume from one PV to another. Let's say we've installed a new enormous physical volume and we want to get rid of some of these smaller ones. How can we? Do we know what physical volume our logical volume is actually using? And what if our logical volume is doing something mission critical and the boss won't authorize any downtime? With LVM, it's actually very simple. Physical volume, move the logical volume named LV0, the -n flag tells pvmove we're specifying the name, off of /dev/sdb1. This takes a while. Notice that I haven't dismounted anything. It will tell us the progress while this happens. If I'd just added an SSD to my system, and I wanted to move my root file system logical volume to it, I could have specified to use that specific device. I didn't in this case because I don't care where LV0 goes, so long as it's not on SDB1. Now we can remove the physical volume from the volume group, which we can do the same as before with VG reduce. Then we remove the drive from the LVM system completely using PV remove. ls our logical volume still looks good. And our file still works. I've covered only the basic topics of LVM: physical volumes, volume groups, and logical volumes. Depending on how you set your logical volume up, LVM can do a lot more. LVM can do volume striping, where data is spread out amongst multiple PVs for performance, or mirroring, where multiple PVs have copies of the same data for redundancy. Each of these special configurations, and many more besides, have different considerations, different actions you can and can't do, and it's all very well documented online and in the man pages of LVM. Holding it all together, FSTAB. In Linux, everything is a file, or at least it looks like a file, and it's all accessible from the directory tree. External devices are automatically added to the directory tree by the udev automount system, and virtual file systems get there from Linux itself. When you boot the system, however, something has to connect the root file system, the swap file system, /home if it's in a separate file system, and so on, together to start the directory tree. Well, this is Linux. There's a file for that. It's called FSTAB, and it's what this video is about. In Linux, the FSTAB is normally found in /etc. Here's mine. There's not much in it. This virtual machine is a simple beast, but let's look at what is here and see what it means. We know from reading df-h that this system has one file system mounted, /dev/sda1, which is the root file system. We know from parted-l that there's a second file system, the swap file system, that we can't see. So here they are in FSTAB. Let's break down what we're seeing. This is the file system identifier. It can be any number of things. It can be the device driver plus the partition number, or device file as they're properly known. My Raspberry Pi does it this way. Here, I'll show you. All device files. There's 1, there's 2, there's 3, there's 4, and there's 5. The file system identifier can be the UUID of the partition, which is how Ubuntu prefers to do things. It can be some other identifier, like one you give to the partition when you make it. Whatever it is, it needs to be something that uniquely identifies this partition. So, which identifier should you use? It depends. Some identifiers travel with the file systems. UUIDs do, except that VFAT and some other older file systems don't really have them. This is for my desktop Linux machine. And this is not a real UUID. It's a volume serial number. If I move this file system to another drive, Mount won't find it. On the other hand, I'll have also moved my bootloader, so I'm probably out of luck anyway. Some identifiers do travel with the partition. Partition UUIDs and partition labels do. Device files can come up different if UDEV happens to recognize another USB drive before the one you wanted. There are pluses and minuses to all the different ways of identifying the partition you want. I tend to stick with however the Linux distribution's installer did it. For UUIDs, to get the UUID associated with a given file system, use block ID. Without any parameters, block ID will show all the block devices, usually file systems, that are connected to the system. This should correspond exactly to the output of parted -L. There's the device name, there's the type, and the partition UUID. You can also look up UUIDs or labels to get the device file names with -U or -L flags. And you can see, giving it this UUID gives us dev SDA1. The next parameter is comparatively simple. It's the mount point you intend to mount the file system to. Just like with manual mount, this is a directory, and it must be there when mount is called or your file system can't mount. After that comes the file system type, just as though you were doing mount -T. Obviously, you have to have a driver in the system for that file system. You can get a list of what file system types your Linux installation understands. You can pipe this through grep if you're looking for a specific one. That's the simple stuff. Let's take a quick break, and when we come back, we'll dig into mount options, FS frequency, and FSCK order. Welcome back. In the last video, I introduced the topic of the FSTAB, and we went over file system identification at some length, and then mount points and file system types. In this video, we'll look at the rest of FSTAB's parameters, mount options, FS frequency, and FSCK order. All file systems are not created equal. Some file capabilities are fine on the root file system, or any other file system controlled by the system administrator, but had better not be usable on floppies or flash keys, and vice versa. Mount options allow you to fine-tune what can and cannot be done with a given file system. The options can be specified in /etc/FSTAB or from the command line using mount. There are literally hundreds of mount options, and they vary from file system to file system, so I'm only going to cover this small handful of the ones you see most often. You can find a larger list in man FSTAB 5 and the full list in man mount. The auto option allows a file system to be mounted automatically when the system boots. It's appropriate for file systems that are permanently connected to your Linux machine, like root file system. Async is also a default option because it allows caching and other mechanisms to work on file system activity in their own good time. Sync forces any reads or writes to happen right now, like DOS did. It's convenient, but slow. It's best for floppies or maybe flash keys that might be removed without dismounting. Default is a list of options that keep most file systems out of trouble. They're listed in this table, but they may vary from Linux distribution to Linux distribution. Dev allows device files to function. Again, on the root file system, this is necessary. Allowing users to create them on flash keys and insert them into the system is a bad idea. Here's why. Modern Linux systems /dev directory is a device populated by udev. Remember how those /dev/sdb and so forth device files pop up when you plug in a flash key? In the old days, you did that by hand with makenode. If somehow an intruder managed to get makenode to work for them and create makenode in a file system other than /dev, it could go unnoticed and be very hard to find, and then they can set privileges on that device file to whatever they want. By setting the file system no dev, Linux will ignore these device files. In a similar vein, exec allows programs to run from the volume. No exec doesn't. If an intruder writes a script in a file system set no exec, it won't run. No boot wait lets the system go ahead and boot even if this file system isn't connected. Bad for root file systems, good for a flash key. No fail prevents errors from being reported if a file system fails to mount. This will be appropriate to a floppy drive prior to the UDEV system, where the device file would exist, but the drive wouldn't do anything without a floppy. Setting no fail meant the failure to mount would be ignored. RO/RW, read-only or read-write. These are hugely important. If a file system is set read-only, nothing, no level of privilege, nothing at all, will let this program write to that file system. It's important because as the system boots, which we'll cover later, it starts out with the root file system read-only. It can make the system hard to work on when it breaks if you don't know that, and you don't know how to change that status. SetUID is another security setting. Programs with SetUID bits can have elevated privileges set. We'll cover this later too. If you plugged in a flash key with a SetUID program on it with the right ownership bits, and if that program happened to be bash, you could have a super user shell. Now you know why outside drives better be mounted with no SetUID. User/no user is, again, more useful in the days when a device file lingered even when the device wasn't connected. It allows mere mortals, instead of super user, to mount that particular file system, and if they mounted it, only they or the super user can dismount it. FS frequency, this one here, is a value that determines whether the dump utility should process this file system or not. Dump isn't installed by default, at least in my Ubuntu virtual machine, but it can go through an ext4 file system and make either a full copy or a copy of any changes since that last dump. See man dump for more details. Dump doesn't work very well on file systems that are running, so there are better choices for backup software. A setting of 0 means this file system shouldn't need dumping, and if you're not using dump, they should all be 0. FS Passno, here. Like FS frequency, this setting is for specific software. Unlike FS frequency, that piece of software is mission critical even today. That software is FSCK, or File System Check. FS Passno determines what order the file systems on this volume should be processed in when FSCK is running. The root file system should have its FS Passno set to 1, and all others on the same volume should be set to 2. Although if there are other file systems on separate volumes, they'll run in parallel anyway. If FS Passno is 0, FSCK will ignore the file system. Let's take another short break. When we get back, we'll go ahead and edit the FSTAB file on this virtual machine and wrap things up. Welcome back. In the last video, we covered mount options and the FS frequency and FS Passno parameters of FSTAB. In this video, we'll go ahead and edit the FSTAB of my virtual Ubuntu machine. I prepared a flash key with a file system. When I plugged it in, UDEV created the device file and automount mounted it. So first I had to unmount it. I want this someplace specific in the file system. First, we need a mount point, someplace public. Let's put it in /home with the assumption that we're putting someone's home directory on it. Normally we'd set this owned by whoever's account will live in it, but we'll leave it owned by root for the time being. Next, we need the UUID of the flash key. This is especially important for flash keys since UDEV assigns them their device files in order of their appearance. Here's the device I'm looking for, /dev/sdb1. And here's the UUID. That UUID is a big handful of numbers. You could write it down, double check it, and retype it when the time comes, but this terminal program does have copy and paste, so we'll just use that. It's always a good idea to make a copy of the FSTAB when you're editing it. If you make a mistake and realize it before you reboot, you can put the old one back in place of the new one, or fix it after the fact with disaster recovery methods, which we'll cover in another video. If FSTAB has severe problems, the system may not be able to boot. Check your work. So I added the line for our drive. I identified it by its UUID. I told it to mount it at /home//home. Told the system that it's an ext4 file system. Mounted it with no exec and no boot wait. Never dump it. And FSCK this file system first when this volume is checked. Normally, you would use the mount-A option to test this to make sure everything works. Let's go ahead and do that. And there it is. But let's see it really work. Let's reboot the system. It's a virtual machine. This takes a moment. Now let's cd to the file system's mount point. Got a lost and found. Let's make a script file. Better yet, let's copy a script file from my home directory. This is what the file should do. And even though I told it to execute as root, we got permission denied. Let's make sure it's not just the script. It works just fine here. In the old days, anytime you added or removed a file system, even a network file system, if you wanted it mounted at boot time, you were mucking about in FSTAB. It still connects the most important parts of the directory tree together, and while there are utilities that replace it, all the Linux distributions I've ever seen still have it. In 1991, as it remains today, the GNU project to replace all of Unix's internal components with open source equivalents was without a useful kernel. Most of the user space parts were in place, command shells, compilers, and so on. But the kernel was stalled. Then along came a guy named Linus Torvalds. He invented a kernel, plugged it into the GNU user space, and Linux was born. You've heard this story before. But what is a kernel? For a program to run, it needs two things, memory and CPU cycles. It's helpful to have I/O, things like drives and screens and keyboards and all that, but it must have memory to store the program, memory for any of the program's variables, and CPU cycles. In ancient microcomputer operating systems, and by ancient I mean I used them in high school and college, your operating system was basically some libraries and a set of device drivers for your specific hardware, because tailoring programs to individual hardware setups got old really fast. You started up your computer, and you either got a command shell, DOS and CP/M had this, or a basic language prompt, Commodore 64, Apple II, and so on had this. Either way, you could tell the computer, load this program. The command shell would hand off to a program loader. The program loader would load the new program into memory, quite possibly right over the command shell, point the CPU at the beginning of the program, and boom, the program started. How did the operating systems of my youth fit into 64 kilobytes of RAM and still get work done? There wasn't much to them, and you ran programs one at a time. The Linux kernel is a program. It runs on the bare metal of the computer like everything did in the old days. It lives in a special protected area of memory. It provides data structures called processes to hold other programs and to hold the program's variables and so on. It provides a way to schedule which programs get to run when, including itself. It provides inter-process security. It protects memory, so my programs don't mess with memory your programs are using. It mediates access to most device drivers, so if you're writing to a file, I don't mess it up trying to write to my own file. In short, it provides each running program a way to have memory, CPU cycles, and I/O, just like those single-tasking computers of old. And it switches between these running programs, or processes as they're more properly called, so fast that they appear to be running simultaneously. In today's multi-core, multi-CPU systems, they really are. That, and more, is what the Linux kernel is. Processes and daemons. Everything in Linux is a file. Everything that does anything in Linux is also a process. And this video is about processes and their enigmatic subset, daemons. So, what is a process? A process is a data structure in the kernel. Each process contains information, including a program to be run, when to run it, and so on. Processes are, by definition, user space constructs, meaning they don't run as part of the kernel runs them. By now, it shouldn't surprise you that a process is also a file. Don't believe me? Here they are, every process in the system in the /proc directory. There's a lot of other stuff in /proc, which is why we've got grep looking for numbers only. Let's look inside a process. PS will give us the process ID of our own bash shell. That's that one right there, 2694. CD to /proc/2694 to go there. ls to take a look around. What program is running will be a symlink from exe. We can see that with ls-l. There's the program that's running, bin bash. What's the process's status? Sleeping, actually. How can that be? When we typed more on our bash command line, the bash process itself forked. It made a copy, told it to load the more program as its executable, connected standard in, standard out, standard error to the new process, and since we didn't tell bash to keep going, bash went to sleep, waiting for more to return. When more returns, it calls a function called _exit to tell the kernel is done. Its parent process, since it's been waiting for that, will get the more process's exit status, and the more process will die. If we'd told bash not to wait for more to return, and we'd closed the bash session in the interim, more would be an orphan, but not for long. It would be picked up probably by init, or upstart, or systemd, which are the processes that start all the others. And they would do the waiting for more's exit status. All processes except init, upstart, and systemd, depending on which system you're on, go through this life cycle. Most of them so short we barely notice they're there. A process's entry in the kernel process table contains a lot of information to give the system and the system admin control over how the process runs, when it runs, if it runs, and whether it should live or die. A lot of the information contained in that entry is identification. There's a process ID number, a user ID number for the process's owner, an effective user ID. When a program has setuid bits on it, the effective ID won't match the user ID. It should otherwise. The effective ID is most often root. Group ID and effective group ID do the same thing, only for groups. The PPID is the identity of the process that forked this one, or more precisely, who this process should report to when it exits. But wait, there's more. The process lists the address map of the pages the process is allowed to use. If it leaves those pages, the kernel will yell at it with a segfault signal. The process status is listed. It can be runnable, which means either running or waiting for CPU time, sleeping, as we saw, stopped, which means it won't run at all without further notification, and zombie. Yeah, processes can be zombies. When a process completes and tells the kernel it's ready to exit, if no process is waiting to get its exit status, the process can't exit, and so it becomes a zombie. Fortunately, in modern Linux, zombies are very rare. I haven't seen one in years. A process also contains a nice value. This value is how nice this process is to all the other processes on the system, or its execution priority. If it's low, it's not very nice, and it will force other processes to wait until it's finished before giving up its resources. The nice value is more of a suggestion to the kernel than a rule per se. Altering a process's nice value is something you used to have to do a lot. Today, not so much. And then there are threads. Imagine you're building a robot. I've done this. Imagine your program needs to do the following things: listen to a sensor, determine the direction the robot is moving, manage the wheel motors, and write to a file. You could do all this with processes, and in the old days of Unix, that's how you did it. Threads didn't exist, but there's significant overhead to creating processes. They take compute time and memory resources, and if you want each of these functions to communicate anyway, why go to the trouble of making them separate, then more trouble to make them communicate? Today, you have threads for this. Threads are part of programs that can run simultaneously within the confines of a single process. One thread can watch the sensor and signal the others when something changes. One can run each wheel motor. One can write to the file. They all share one set of memory pages, so they can read and write to each other's memory. They're not required to be separate executables. The killer benefit that is responsible for multi-threading spread into everything is that if your computer has multiple cores or CPUs, those threads can be run at the same time. It's complicated programming to be sure, but as a Linux system administrator, you need to at least know what threads are and what they look like. So let's go look at some threads. I've told PS to list all processes and all identifiers. Over here, you can see the process IDs. Note how they repeat. Here's 451, rsyslogd. Each thread inside a process has its own ID here. So here's 451, 455, 456. Those are thread IDs. They are in the column LWP, which stands for lightweight process. Here's how much time each thread is taking up, not much in this case, and how it got started. Unless you're writing multi-threaded programs, managing threads is usually done at the process level. If a thread runs amok, kill the process, which we'll talk about next. We've covered a lot of ground and it's complicated. These are the guts that make up a Unix-like operating system. So let's take a break, and when we get back, we'll dig into managing processes. Welcome back. In the last video, I introduced the concept of processes and went to some length about process anatomy. Plus, we looked at some processes in the most raw form available. In this video, we'll dig into tools for managing processes. PS lets you look at lists of processes. It takes an enormous number of flags, and you can pipe its output through grep and other utilities. It's been around forever, and the PS we have today merges several different Unix dialects of PS, so a number of flags do the same things. By itself, PS lists only my processes, that is, the ones running under my login right now. PS-E gives you every running process on the system. You can pipe it through more if you want to browse the entire list, or you can pipe it through grep and look for something specific. Different flags specify what statistics you want to get on each process. There are dozens and dozens covered in the man pages, but a few combinations are so useful they're worth memorizing. If you want statistics and you want to see what commands started those processes, PSAUX is the one you want. That is the user. Here are the statistics. Here's when it started, and that's the command that started it. I've installed MPD, the music player daemon, on this virtual machine. That way we have a server we can stop and start with impunity. There aren't any actual music files on this virtual machine, so there's nothing to hear. We'll cover init, which the service command is part of, later. For now, what's important is that it starts and stops daemons that are configured for it. The MPD server or daemon is running. Here it is. I've piped the output of PSAUX through grep, so I don't have to wade through the whole process list and look it up myself. That's a job for a computer. PS has some other interesting options. If you'd like to see what process forked itself to start a given process, you can use PSFAUX, or PSFAX, or PSTree. I found it useful to redirect the output of PS-FAX to a file and search it in nano. It doesn't respond to grep well. Here's MPD, and if we follow it up far enough, its parent is upstart. You can change what a process is doing or shut it down completely with signals. Signals are sent to a process to alter its settings. Signals can be masked by a program, that is, it can tell the process to ignore certain signals. Signals can also be handled when the program is designed to catch them and do something about them instead of relying on the kernel to do it. Signals are sent to processes with the kill command. We'll cover 5 of the most basic signals. Signal 1, sighup. This has 2 distinct functions. For a process connected to a terminal, like a bash process, it signals that the terminal has hung up, perhaps by being switched off or a modem drop, as in phone modems. That kind of thing happened a lot. For daemons, that is, processes not tied to a terminal, sighup is usually handled and used to force the server to restart and reload its configuration files. This is the old way of restarting a daemon, and there are better ways now, but it still works. Signal 2, sigint, an interrupt. You send this signal every time you hit Control-C on an app in the terminal window. Signal 3, sigquit. Exit if you can, close your files, clean up, and produce a core dump. We'll get into core dumps later, but they are a debugging file to help you figure out why a program is crashing. You force a process to dump core because you want to look at what's in the process memory without any further changes. Signal 9, sigkill. This tells the kernel to terminate the process without further discussion. Sigkill can't be masked or ignored. The process never even sees it. If the process has files open, they'll be left open, which makes a mess. The antithesis of sigkill is sigterm, signal 15, which asks a process nicely to close its files, wind up its business, and shut down gracefully. There are a number of different tools that do the same job as kill, such as kill-all. Most of them automate some or all of what I'm about to demonstrate. I'll use kill here to make clear what's happening. First, let's find MPD and send it a sighup or signal 1. See how there are 2 processes? Look at them carefully. This one was started with the command grep --color equal auto MPD. It's not the MPD process at all. It's me grepping for the MPD process. We can ignore it. It's already gone. This one was started with userbit_mpd and /etc/mpd.conf as its parameter. It's the one we're looking for. I've sent it a signal 1, a sighup. You can see that it's still there and the PID hasn't changed. We'll have to take its word for it that it reread the configuration file. Not all daemons do it correctly. I'll send it a signal 2 next, but I'm going to send the signal by name. You can see the process has terminated. As a daemon, it didn't have to, but it has. I'm going to skip signal 3 because I don't need to generate a core dump, and reading them is something we're going to touch on extremely briefly later. As you can see, I have restarted MPD, and it has a new process identification number here. I've gone ahead and hit poor MPD with a kill -9. It doesn't look any different from the other times we've terminated MPD, but if MPD had a playlist it happened to be writing when we terminated it, that playlist is now trashed. Kill -9 is the weapon of second to last resort when a process runs amok. The next step to take, on the rare occasions that kill -9 doesn't get the job done, is rebooting. And after that, the power switch. You're the system administrator, the system must obey you. Let's take another break. This time, I'd like you to poke around at the processes running on your system. You can install MPD yourself and poke at it, or if your system is just a practice machine, poke around at the other processes and daemons. If you hang or crash the system, reboot it. It should be okay. This is how we learn. In the last video, having understood what a process is, we looked at a number of tools for monitoring processes, and we looked at tools for managing processes. Killing them is managing them, yes. In this video, We'll look specifically at that most unusual class of processes, daemons. What is a daemon? It's a process that is parented to init, or, in modern Linux, upstart or systemd. It is not controlled by a terminal. Its output usually goes to a log file, which we'll cover later, or to a device file called /dev/null, which throws it away. A daemon provides a system-wide service. MPD is a great example, but the Apache web server, the email server SendMail, LogD, SSHD, Avahi daemon, the inetd aggregated internet server, and so on, all do similar things in similar ways. Each daemon's configuration is different, and usually they have their own configuration file. Since daemons are usually logging and often have connections to hardware, they also need to be started and stopped in a controlled fashion rather than simply killed. And somehow, there must be a provision to start them at boot time. We're going to look at MPD's configuration files since they're relatively simple. Finding the config files is another job for Whereis. Here's the MPD program, and there's its config file. Different daemons call their config files different things, and the location of the config file is usually in the man pages of the daemon. If not, a web search will uncover it. Daemons are not required to use any particular format in their config files, but the convention is that hash marks are comments. Here's the directory MPD expects to find music in. Here's where it puts its databases and its log file. Here, you can see that MPD has the option to run in its own account. Daemons can do that. This is important for security. Not all daemons need or should have super user privileges. MPD certainly doesn't. So when it's started, it effectively gives an su mpd command, switching users to MPD. Because init is run with super user privileges, it can do that without an additional password. MPD can be a network server, allowing you to control the playback on this machine from other computers. Here's where we set up its network settings. Lots of settings on logging. Here's where you set whether MPD requires a password to connect to and what MPD will allow an unlogged-in user to do. After that is hardware configuration to allow MPD to communicate with audio hardware on this specific distribution and this specific machine. That's how daemons are. They can be generic because the tailoring happens in their config files. Reading the config files will sometimes give you more and better information than the man pages do. Good ones, like MPD's config files, include examples too. Until recently, daemons were all started with the sys5 init system, or simply init. And on most Linux distributions today, init still does a lot of the heavy lifting. The Raspberry Pi distribution Raspbian, for example, still uses init exclusively. We've been starting MPD with init syntax. Here's how you do it. Init is controlled by scripts. Here are the scripts that make that happen. They all live in /etc/init.d. You can see a lot of jobs are still handled by init as of Ubuntu 14.10. MPD's init script looks like this. In the comments, it lists what run levels it starts at and what run levels it stops at. So what, you wonder, are run levels? The init system has a number of different levels. 0 is halt. When the system is at run level 0, the kernel is not running. Init 1 is single user mode. The kernel is running and you can log in, but none of the services are running. Init 2 is local multi-user with networking, but has no servers running. It's much easier to fix a Linux system if you have access to the network. Init 3 is full multi-user with networking. Init 5 is full multi-user with networking and X Windows, which is the graphical user interface. And Init 6 is reboot. The big criticism of the init system is that it's dumb. It was designed in the days when Unix hardware was static. It also isn't good at parallelizing. To run startup processes in parallel, you have to know which processes need to start first, one at a time, and which ones depend on other services but are not dependent on themselves, so they can be started at the same time, and script accordingly. In short, it relies a lot on system admin know-how to keep it running. In the last few years, movements have been afoot to replace the sys5 init system, which dates back to 1983. The dominant replacements are upstart and systemd. Upstart replaces all the startup scripts with configuration files. They live in /etc/init. LightDM is the display manager service for the GUI. It allows logins and automatically logs you in. On this Ubuntu virtual machine, it started by upstart. You can see a big difference from the init files. First, it's not a script exactly, it's a config file. Here, it lists the condition LightDM requires to run. Run level 6, dbus has to be started, Plymouth Ready has to be set, Here are the levels at which it is to stop, 0, 1, and 6. And here, it has 3 event scripts, startup, post-start, and post-stop. These will be triggered only when one of those events happens. Here's LightDM's status in Upstart. We're going to restart LightDM. This will bring the whole GUI down for a few seconds. You could also command it to stop by replacing restart with stop, or to start by replacing restart with start. In 2014, the Debian Technical Committee voted to transition again from Upstart to systemd, which is another replacement for init. Since Ubuntu is a Debian-derived distribution, it is transitioning from systemd to Upstart. As of Ubuntu 15.04, Ubuntu will come with both, but with systemd as the default. Since Fedora already uses systemd, we'll use it for this next demonstration. I've installed MPD on my Fedora virtual machine as well, and as you can see, I'm su'd to root. The syntax is remarkably similar. There's MPD. I'm using the systemctl command. And now you can see MPD is gone. And now I've started it again. And now I've restarted it. All the changes we've made so far are temporary. They'll go away when the system reboots. To configure systemd to start a daemon at boot time, since we're here, the command is systemctl enable, in this case, MPD. And to disable it, in Upstart, as in init before it, the easiest way to enable or disable a service is to move the associated file out of the /etc/init directory for Upstart and the /etc/init.d directory for init. We've covered a lot of ground in this set of videos, and there's a lot more we could talk about. There are a lot of good books and websites on the subject, but process anatomy evolves quickly as Linux progresses, and the mechanisms for starting and stopping daemons are in flux. Make sure your sources are as up to date as possible. Virtual memory. Why virtual memory? In 1972, Unix was still in diapers, and a RAM company called Intel had just released their very first microprocessor only the year before. That year, my parents bought the house I grew up in for a little less than $20,000. That same year, a megabyte of RAM cost about 400,000 of those same 1972 dollars. That's about 2 million 2015 US dollars. Multitasking takes lots of RAM. For Unix to thrive, it had to have a way of using less expensive disk storage for part of its RAM. This is called virtual memory. By 1991, when the Linux kernel was released, the price of a meg of RAM had fallen to less than $50, but still, for a student or a hobbyist early in his or her career, RAM was expensive. It still made sense for Linux to have virtual memory. RAM is cheap today, a little more than half a cent per meg, but virtual memory is still with us, it's still useful, and it's what this video is about. So, what is virtual memory? Virtual memory is simply this, an abstraction that separates system memory from the physical hardware of RAM. If that sounds like the abstractions in file systems that we see with partitions and LVMs, that's because it is. The biggest use of this abstraction is to let cheap disk storage take the place of RAM that has stuff in it, but is not actively being used. In the old days, this meant a process that was sleeping or not scheduled to get any execution time soon was swapped out and the RAM released for other processes. Today, memory is broken up into pages, and it is those pages, as decided by various threads in the kernel, which are paged out. By default, a page is 4096 bytes. Virtual memory is built around CPU capabilities, and different CPUs can handle different page sizes. Because Linux is cross-platform, meaning it runs on lots of different CPUs, exotic large sizes aren't used by default, although modern Linux supports them on appropriate platforms if you turn them on. The life and states of a memory page. There are a number of structures in Linux's virtual memory system that I'm going to gloss over. Slabs are contiguous areas of memory held in sections so the kernel can allocate them quickly, instead of having to search all of memory for what it needs. Buddy blocks are contiguous blocks of memory in power of 2 sizes, sorted from small to large, to keep memory defragmented, and so on. But the fundamental structure is the page. The page has 3 stages in its life. It begins free. It's allocated to a process, or to a cache, and then it becomes active. Things get complicated. The kernel knows when a given page is accessed. If it's not accessed in a while, the page becomes inactive. Inactive pages are subject to being paged out to the swap file if memory demand is high, a calculation done on a number of variables. The swapping is usually done by kswapd, a thread belonging to the kernel. If a process calls up an address on that page, it generates a page fault, and the kernel swaps that page back in. If the process exits or otherwise frees all the addresses in its page, that page becomes free again. This is vmstat. I've passed it a flag minus capital S and capital M. This changes VMStat's output from JEDEC kilobytes to JEDEC megabytes. Be aware that if you use lowercase k or m for the units, it will give you Weasel units. This is the number of runnable processes waiting for CPU time. None. This is the number of processes which are uninterruptedly sleeping. None. SWPD is the amount of virtual memory being used. None. Normally, this is 0. RAM is cheap, and we have lots of it. Free is how much memory is not being used, and these are megabytes. Buff is how much memory is being used as buffers, which store data for future use. Cache is how much memory is being used to cache our file systems. SI and SO, respectively, are swapped in and swapped out. This is how active your paging system is. They're called swapped in and swapped out for historical reasons. If you see a lot of page out events here under swapped out, it means your system does not have enough RAM and you're paying a huge performance penalty as it pages to disk. If it's not the normal state, that's fine. That's what the page file is for. If it becomes chronic, you need more RAM. VMstat can sample repeatedly if we tell it how far apart to put the samples, and it can sample a specific number of times if we give it that number. Here I've told VMstat to sample every second and to do it 5 times, so we can watch the trend in virtual memory. If you want to look at other structures in the virtual memory system, like slabs or buddy blocks, there are VMstat flags to do that. See the VMstat man page for more information. Virtual memory stats are useful, but if you're low on memory, some process is using that memory. To find out which one, use top. Top is a dynamic display. It samples every few seconds and runs forever unless we tell it otherwise. Top does consume significant system resources, so don't leave it running if you're not using it. What top does is shows you a list of processes in order from greatest resource users to least. Top gives you a lot of information. What time it is, how long it's been since the system was rebooted, how many users are logged in. Wait, I know you're thinking it. How can there be more than one user on the system when I'm the only one on? Top counts open terminals as users, so I have one for my GUI and a second for my terminal. Load average here. If this number is above 1, it means you have processes waiting to be executed, so you're processor bound. Number of tasks here, 170, of which 1 is actually doing anything, and 169 are in non-interruptible sleep. Stopped processes are ones that Linux has been told not to run at all, but not to terminate. And zombie processes are here. Next are CPU statistics. This is cumulative for all the cores on my virtual machine. If we press 1, we can see how the statistics break out for each core, but my virtual machine only has 1. Here's the actual RAM. Here's the swap space. How much is used, how much is free, how much is being used as buffers, and how much is being used as cache. Like most Unix-like operating systems, Linux will usually use quite a bit of memory for cache, but if memory gets tight, it will shrink the cache, degrading file system performance a bit in exchange for program performance. Now we get to the process data. Here's the PID. The user is who owns the process. A process, like everything else, is also a file, so it has an owner and permissions. %CPU and %memory are the resources these processes are using. Time plus is the amount of time each process has spent on the CPU, not how long it's been running in real time. And command is what commands started the process. Some programs are not very well written and will slowly leak memory or get stuck and burn up a huge amount of CPU cycle. They'll show up here in the process statistics section. Web browsers are notorious for memory leaks, so if you see Firefox or Chrome at the top of this list with some huge amount of RAM used, you can restart the program and get that memory back. We've covered a lot of ground. Let's take a short break, have some coffee, and let all this soak in. When we get back, we'll dig into swap files, swap partitions, and tuning the virtual memory system. Welcome back. In the last video, we covered the rudiments of what virtual memory is and how it works, and what tools there are for managing memory consumption in general. In this video, I'll show you how to expand your system's virtual memory in the cheapest way possible by adding a swap partition or a swap file, and we'll talk a little bit, a very little bit, about tuning virtual memory. When virtual memory pages aren't free and they're not in RAM, they're in swap space, which is on a file system someplace. Swap space can be in a dedicated file system, whether on a physical volume, a partition of a physical volume, or a logical volume. Once upon a time, this was the only way to get swap space in Linux, and if you were smart, you put the swap file on a separate physical volume from the rest of the operating system for performance. Now you can put it in a partition on the same physical volume, or on a logical volume. Swap space can also be a file inside another file system. Old-time Linux users sometimes say this incurs a performance hit, but with modern kernels, it's not really true anymore. I've connected an external drive to my virtual machine. USB isn't really ideal for swap space, but this is just for demonstration. My drive has connected at /dev/sdb, so I point parted at that. Print the partition to make sure I'm looking at the right volume. Yep, that's the one. Set the unit to gibs instead of Weasel gigabytes. Now, I'm looking at this volume, and we can see it's got one partition called boot that is an ext4 partition. We'd like to put a swap partition on it. There we are, 1 gib of free space. We'll put it there, but we're going to have to switch units to MIBs. This is a small drive. But I'm telling parted to make a partition called test of the type Linux swap from MIB 903 to MIB 1927. If this were a real swap partition, we would want to align it for best performance, but this is a demonstration. And there it is. Now we exit out of parted and type make swap /dev/sdb2, which must be done from superuser. Now we enable the new swap file system. We can use swap on to list what swap partitions there are. There's the original, there's the new one. In order for the swap partition to be activated at boot, we need to add it to /etc/FSTAB. So we edit it. And we add the swap device. We can use the UUID, but let's do it the easy way with the device file. No mount point. It is a swap file. It is of type swap. Tab 0. It is not to be dumped. Tab 0. It is not to be FSCK'd. Save it, and we're done. That swap partition will come back when we restart the system. I'm not actually going to save the FSTAB changes, since this is a removable drive and I don't actually want a USB thumb drive for a swap. To remove the swap partition, we use swap off. As you can see, our swap drive is no longer present. Swap files are even easier. Let's put one on the same drive in the other file system. CD to the mount point. Fallocate is a utility that allocates a contiguous group of blocks on the file system. We need that to put the swap file in. Be advised that Fallocate works in decimal numbers of bytes only, Weasel units, so we have to specify the closest decimal approximation to get a real 512 MIBs. We need to set the permissions on the file. We'll cover permissions at more length in another video. Only root should be able to see the contents of this file, so we set it so only root can. Create the swap space in the file, add it to swap. There it is. /etc/FSTAB works much the same way. Just give it the full path. Mount point none. Type swap. Flag SW. Tab 0 for no dump. And 0 for no FSCK. And once again, I'm not going to save it because having a file system that's required to boot on a USB connection isn't a good idea. Removing our swap file works the same way. Now we just delete the file. Let's take another short break. When we come back, we'll look at tuning the virtual memory system. Welcome back. In the last video, we talked about swap files and partitions and how to make them. In this video, we'll wrap things up talking about tuning the virtual memory system, and I'll cast a vote for leaving the defaults as they are. There are lots of variables you can tune in the virtual memory system. Here's the list. Enterprise Linux systems come with lots of tools for generating statistics to tweak those settings for the absolute best performance or most resilience, and so on. And there are even more suggestions out there on the net of cookbook setups for tweaking your virtual memory system. Realistically, the default values seem to work pretty well, so I'm going to show you one setting, how to check it, and how to make it permanent. Just one. It's called vm.swappiness. vm.swappiness encourages the kernel to leave pages that are only in RAM, and to preferentially swap out pages from the various file system caches. It's set to 60 by default in Ubuntu and Fedora, and 1 in Raspberry Pi's Raspbian, which reflects that all of Raspberry Pi's I/O goes through the USB system or to an SD card, where you need all the performance help you can get from the cache. If you have a virtual machine or an SSD, set the swappiness to about 10. Here's how you do it. At the end, add these lines. Comment so we can find this line later, and the actual line, vm.swappiness equals 10. Close the file, reboot, and it's done. I tried this on my desktop Linux machine. If it made any difference, it made things slower. Your mileage may vary, but do take internet advice with appropriate skepticism, and remember that if the advice is more than a year old, it may not apply to your system at all. Still, The point is, you can tune the virtual memory system, and if you are adapting Linux to very special needs, like the Raspberry Pi and its slow I/O hardware, or you have statistics that tell you your system is swapping too much or too little, it's valuable. I'll stick with the defaults. In Linux, everything is a file. This means that nearly everything is secured like a file too. So it's absolutely crucial to understand the Unix Linux file system security mechanism. Fortunately, it's not all that complicated, and it's what this video is about. Owners/user, group, and world/other. Every file and every file-like object in the file system has a mode or permission field in its inode. Every file also has an owner ID. The owner is the account that really owns the file. There can be only one owner. Every file also has a group ID. While only one account can ever own a file, a group can contain multiple users, and a user can be a member of multiple groups. These IDs are also stored in the inode and assigned when the file is created. Normally, they are inherited from the owner and group of the process, which itself is also a file, but they can be changed using the chown and changegroup utilities, which I'll demonstrate later. It's important to understand that the file's owner and group are distinct from its permissions, as you can see from the output of ls-l that I've pasted at the top of this slide. That's the owner, that's the group, and that's the permission. They're separate fields. Permission classes and mode bits. There are 3 general classes of permission on each file: owner/user, group, and other or world. The owner is the user ID listed in the file's inode. The group, likewise, is the group ID listed in the file's inode. Other or world is everyone else in the system. Each class has 3 mode or permission bits: read, write, and execute or search. Read is exactly what it sounds like. The file can be read. If it's a text file or a data file, that's all that's required. Write is also what it sounds like. The file can be written to. In Unix-like operating systems, this is also permission to delete the file. Execute means the file is a program and can be executed. If the file is a directory, executes meaning changes. It means that the directory can be scanned. That class of user can ls the contents or cd to the directory. So looking at the output of ls-l that I've pasted in above, we can see that the owner/user is root. The group is also root. The owner can read, write, or delete, or execute /bin/ls. Anyone in the root group can read or execute /bin/ls, and anyone in the rest of the system can read or execute /bin/ls. The kernel enforces these permissions when any access of the file is attempted. If your process doesn't match the permissions for the file access it's trying to do, permission to access the file is denied. As you can see, my account is not allowed to access /root, not even to see what's in the directory. Looking at the permissions, we can see why. Access is locked down to the owner and only the owner. Remarkably few programs in Linux actually depend on lockdown permissions to keep normal users out. Instead, most check for privileges when they try to access another file. Here's VIPW, the password file editor. A mortal user like me should not be able to run that, right? Well, I can actually, but when it tries to get a lock to write on the etc password file where the accounts are set up, it fails. Here's why. Only the owner user has write privileges, and the owner user is root. The owner group and permission values aren't cast in stone. They can be set with utilities. Chown changes the ownership of a file. It will run, but it's not useful without root privileges, since it makes a file owned by someone it's not owned by now. Modern chown can also set the group at the same time, but in the interest of clarity, we'll do it in 2 steps. Chown takes the usual assortment of wildcards and flags, including -r, to recurse down through directories. Changegroup changes the group membership of a file. Unlike chown, changegroup is useful for mortal users. We're allowed to change group a file to any group we are a member of. Like chown, changing to non-membership groups requires root privileges. Also like chown, changegroup takes the usual assortment of wildcards and flags, including -r for recursing down into directories. chmod changes the file's mode or permission bits. We're going to spend most of our time with chmod in this video. I've created a file in this virtual machine called test.sh. It's a shell script. Here it is with the privileges it was born with. Owner user, read and write. Group, read and write. World other, read. Let's chown it to root. Now it's owned by root. This changes my perspective to the permissions. I'm not the owner user anymore. Root is. It's still in my group, so I can still edit it or delete it if I wanted to. Let's fix that. It should be in root's group too. Okay, now it's in the root group too. Again, my relationship to this file has changed. I'm not the owner user, and I'm not in the root group. Now I'm world/other. When I edit it now, you can see that Nano will read it, but it's complaining that I don't have write permission. Okay, we've seen that before. Since I'm in my own group and I own this file once again, I can change it to my own group without privileges. Let's take a short break. When we get back, we'll get into some of chmod's many talents. Welcome back. In the last video, we covered how file system security works from the inode level up through the security/mode bits, and we tried out chown and chgroup. Now it's time for chmod. There are two distinct ways to use chmod. The first, the oldest, is in binary. Here's how it works. Each class of privileges, owner, group, and world, are 3 bits from right to left, just like base 10 numbers. The rightmost bit is 1. That's the execute mode bit. The next one to the left is 2. That's the write bit. And the leftmost of the 3, the read bit, is 4. So to set a class with no access, you'd give it a 0. To set a class with all privs, you'd give it a 7. Read only is 4, write only is 2, and execute only is 1. Now put another number for each class, for a total of 3. An example is chmod 755. That's owner user 7, which is read, write, and execute. 5 for the group, which is 4 for read plus 1 for execute. World is set to the same thing. Chmod can also take text-based classes and modes. These are easier for some people to memorize. Here's how they work. There are 4 classes: user, or owner, group, and other, or world, and A for all 3. There are also 4 modes: read, write, execute search, and capital X. As we covered earlier, setting a directory execute means it can be searched or CD'd to. If you set a group of files, either with wildcard or recursive flag, with the capital X mode, directories will be set searchable. Regular files that were already set executable will be left that way, but no other files will be set executable. Here's where it gets complicated. Each of the classes and modes in the last 2 slides can be combined. UGO, for example, is user and group and other, all 3 classes at once. UO would be user and other. Combining modes works the same way. RWX is read plus write plus execute. RX would be read and execute. Modes are additive too. You don't have to specifically set all the mode bits. So if you have a file that's already readable, chmodding it plus X will make it read execute to the entire world. You can also combine the combinations. If you wanted to set the file wide open so user, owner, group, and others would have all permissions, you could type chmod UGO plus RWX, or simply chmod A plus RWX. There's no rule that says you can't set mode bits and clear them in the same statement. So chmod A equals RWX, GO minus W, file name, sets read, write, and execute bits on all 3 classes, and GO minus W takes away write from group and other, leaving the file the same way it was after chmod 755, user/owner read and write and execute, and group and other with read and execute. Let me demonstrate. Here's test.sh with the privileges it was born with. If we want to make it executable for the owner, that's me, we need the owner class to have all its bits on: read, write, and execute. That's 4 for read, 2 for write, and 1 for execute. We'd like to leave the other 2 classes as they are. Group has read plus write, which is 4 for read and 2 for write, so 6. The third class, world other, is read only, so we want that at 4. So our chmod call would be chmod 764 test.sh. Okay, now the execute bit is set. Will it run? It will. Want everyone on the system to be able to run and read it, but only the user owner can delete it? Chmod 755 test.sh. 4 plus 3 plus 1 equals 7, turns on all 3 bits for the owner class. 4 plus 1 turns on read and execute for the other 2. 664 sets it back the way we found it: read plus write for the owner/user, and group, and read only for world and other. Chmod with character modes. All right, let's set test.sh so we can execute it again. There's your execute bit, and it runs. A lot of times you'll see people use chmod plus x test.sh. Not specifying a class is the same as specifying all, or U, G, and O. It gets you all three classes at once. Now there's an execute bit set in user owner, group, and other/world. Whether it's a good idea or not depends a lot on what the file does, but for my money, a world executable file without a good reason isn't good. We can take away the execute privilege the same way, only we'll use the A or all class this time. Got them all. Now let's say we wanted read, write, execute for the user/owner and read execute for the group and other. That'd be chmod a plus rwx, comma, go minus w, test.sh. Add all modes for all classes, then clear the write mode for group and other/world. And there it is. Read, write, execute for the user/owner, me, read, execute for group, and read, execute for other/world. Which way is the best way? Whatever works for you, or you can mix them. There's a lot more we can do with chmod. It's a major utility in the Unix and Linux worlds. We'll have to get some more concepts in mind first, so now's a good time to take another short break. When we come back, we'll dig into setuid and sticky bits, which are also set with chmod. Welcome back. In the last video, we covered two ways to use chmod. In this video, we'll dig into setuid, the ability to have a file effectively run as someone else's, and the sticky or restricted delete bit. When you start a process, your user ID from your account is listed as the process owner. That value is copied from the effective user ID, since they're the same, and that's what shows up in the PSAUX output I've pasted in as a reminder. There's my username, which is translated from the process's EUID by PS. Setuid changes this. When the kernel loads an SUID process, it copies the file owner's ID as the effective ID, and the process runs with the file owner's level of privilege, rather than the person calling it. Here's the PS aux output from a copy of bash I made called mybash that has the setuid set. This is sitting in my account, runnable by absolutely everyone, and it cranks up as root with superuser privileges. Note the username. It might seem like SUID is dangerous and has no legitimate uses, but it's the mechanism that allows sudo and su to work, and assuming they handle their security properly for themselves, that's perfectly valid. Here's su. See the s where the x would be normally in the owner class. That's for setuid. If it's lowercase, which it is, it means this file is executable too, as the x in group and the one in world also make possible. What this means is this program will run with an EUID of its owner, in this case, root. It's the same with my nasty little copy of bash. So how did this thing come to be? Well, let's erase it, and I'll show you. The first thing I need is bash. I know it lives in /bin, so let's try it. Doesn't look like it did anything, but if we look it up in PSAUX, there it is. Nothing special about this copy of bash so far. Next, I need to make it owned by root. We already know how to do that with chown, but we'll need superuser or root privileges to do that. Done. You can see, even though root owns my bash, it still lists itself as run by me, which it should. Now we'll set the SUID bit. We'll do it in binary first. There's an extra 3-bit class in chmod that we haven't talked about. Its bit 1 is sticky, bit 2 is setgid, and 4 is setuid. So to set my copy of bash setuid, and set it so I can execute it despite not being the owner, I need to do something like this, with root privileges. Once again, there's the S set in the owner class where X should be. Does it work? Actually, there's a wrinkle. For bash to execute a command with setuid privs, we have to pass it a flag, -p. We've seen that prompt before. That's the root or superuser prompt. Let's clear the privileges from our superuser shell. Note that we're still in the superuser shell. As long as this process doesn't exit, this shell stays privileged. Once we exit, trying to start it again fails, because the 664 privilege sets the file to not executable. Let's set the same privilege with character modes. That's set user/owner plus S, which is setuid, and A for all, plus X for execute. And here we are again. Setgid works approximately the same way, but it's not as drastic. We're done with mybash, so let's get rid of it. The sticky bit is the most benign of the lot. It does one thing. Set on a directory that otherwise has open privileges, it prevents one user from deleting another user's contents. I've created a directory called testdir. Now I've chmodded it wide open, and I've created a file in it. Now, if I log in as someone else, say my secret alter ego, I can go to that directory and remove the file. That's not good. I might have been using that. Let's set testdir so I can write files in it, and so can srj, but srj can't delete my files. Note the T in the world's other class where the X would normally be. That's the sticky bit. Now it won't let me. I'll create my own file just to prove I can. There it is. Now I'm back as JRS. Since I own the directory, the delete restriction sticky bit does not apply to me, and my alter ego's file is gone. To set the sticky bit with the character classes, surprise, it's not another S. And there's the sticky bit again. That about wraps it up for chmod, and that's most of file security. But there is one more thing: access control lists. Not all file systems have them enabled, but most do. We'll cover them after this break. Welcome back. In the last video, we covered chmod and the special bits setuid, setgid, and sticky. In this video, we'll cover access control lists, or how to give just the privilege you want to just the user or UID you want and no one else. In our discussions of chmod, did you ever wish you could just give one user access to a file without adding them to a group or anything like that? Well, I'm here to tell you that with access control lists, you can. Access control lists give the system administrator or the user fine-grained control. With access control lists, you can allow access to a user or a group and then remove one or the other later without affecting the rest. The commands that control access control lists aren't imaginatively named. They are setfacl for set file access control list and getfacl for get file access control list. Set, as I'm sure is obvious, sets them, and get retrieves them. There are only a couple of catches, mostly to do with older versions of Linux and older file systems. ACLs are comparatively new. You need a kernel since 2006 or so, and a file system of ext2 or better. That's not asking a lot today. If you absolutely can't get ACLs to work, you may need to enable them as a mount option in the file system you're using. setfacl takes the usual enormous number of flags, but here are the most useful three. M modifies an access control list entry. If you're adding one, this is where you do it. X removes an access control list entry and all its permissions. B removes all the access control list entries except the default values. There are lots of others, like -R for recurse through directories, and it takes all the usual wildcards. getfacl also has an enormous list of flags, but it's useful exactly the way it is. ACL entry. An identifier on the access control list is made up of three parts separated by colons: the type, an identifier, and rights, some combination of read, write, or execute. I'll cover the most useful types, but bear in mind there are plenty more. U is the type used for usernames. The syntax is U, username, rights. G is the type used for group names. The syntax is G, group name, rights. These entries should be quoted to keep bash from mangling them. So let's imagine I have a file, test.txt, that I'd like my alter ego srj to be able to edit. First, let's look and see if there's an ACL on test.txt. Nope, those are the default values. Here I am modifying an entry. I am adding a user, srj, and giving him read, write, and execute privileges to test.txt. And there it is. Now, if I log in as my alter ego srj, first let's edit another file. No ACL.txt in this case. Fail. No write permission. We can edit test.txt, however. srj will have a few words to leave. Okay, back in my own account. And there's my alter ego's handiwork. But let's say we want another user to have access. We could create a group, but not if we don't have root privileges. Access control lists work without them. There aren't many users on this machine, so let's add root to the access control list. Now you can see I have two entries, that one and that one. If I decide I don't like my alter ego, I can remove him just as easily. No more access for you, alter ego. Oh heck, I've changed my mind. I'll give you read access only. If I want to remove all the ACL entries on this file at once, there's a command for that. Now we're back to the defaults. But wait, there's more. Want to add a group to the access list? We can do that. Now anyone in the group disk can access the file. Actually, there's a lot more. Access control lists add a mask to the traditional file permissions. You can manipulate the mask directly, you can back the ACL up and restore it, and set FACL takes the usual flags for recursing down directories, following symlinks and hardlinks, and so on. The man page is largely impenetrable, but there are quite a few good websites on the subject. Account anatomy. In nearly every other video in this series, I mention accounts somewhere, or UIDs, or groups. These things don't just happen. They're created, normally by a script. It's easy. You just type sudo, add user, and fill in the blanks. But knowing these tools is like knowing how kittens are made. It doesn't tell you how the cat works. In this video, we're going to build an account by hand from scratch. It's not that hard. Cat biology? That's hard. What's in an account? An account is made up of 6 things. It's an entry in the /etc/password file. This file is world readable. Some unprivileged programs need to be able to read it, like email or the old finger utility that told you who somebody was. The actual passwords are in the /etc/shadow file. An account also needs to be in a group, usually its own. It keeps accounts out of trouble. Membership in other groups can be added later. Because some systems allow you to access a group with a password, /etc/gshadow contains these passwords. Most of the entries in it block the use of group passwords by default. An account needs a home directory. In Linux, these are under /home, but they can be anywhere if the account has permission to access it. The home directory will usually have some default configuration files in it. Finally, an account has a password, which is set with a special utility called password. If an account has these 6 parts, the user will be able to log in and use the system. One other thing, don't just edit /etc/password or /etc/shadow directly. They take a special editor called VIPW, which frankly is dreadful. Fortunately for this demo, we can just echo the lines we want and redirect/append them to the end. So crank up your root privileges, sudo su for those on Ubuntu-based systems and others using sudo, and sudo to root for Fedora-based systems with a root account. Here we go. Here's what's in /etc/password. Here's my account, JRS. Each field is separated with colons. My password is X, which means there is one, and it's stored in the shadow file. My UID is 1000, and my group ID is also 1000. My name is here. This is the one the GUI uses, so it's kind of important. The rest, not so much. Home directory here, default shell here. Make sure you use a new UUID and group ID. My account has 1000 for both, so let's use 1001. Use single quotes around all of this so bash doesn't eat it. So we're adding an account. SRJ has a password. UID and GID are 1001. There's his name. Home directory. Default shell. To etc. password. That all looks right. Here's what's in /etc shadow. If you really wanted, you could type this in and break the passwords on my virtual machine. There's my account. That mass of gobbledygook is my encrypted password. That number is the age of my password in days since January 1st, 1970. The next number is how many days have to go by between password changes. That one is how many days the password is valid, 273 years in this case. It could be 30 days. And that one is how many days to warn me before my password expires. These empty values are how many days after it expires to deactivate my account, or an absolute date the account deactivates in days from January 1st, 1970. So let's set SRJ up. SRJ, there's a password. It has never been reset. There are no minimum number of days between resets. It is good for 273 years. Warn him after 7 days, and don't do anything else. Here's what's in /etc/group. There's my group. It has something in gshadow, It is group 1000, and it has no members. I am the owner, not a member. SRJ needs one of these too. So that all looks in order. Here's what's in /etc/gshadow. There's my group name here. Exclamation point means it's locked. These two fields would be for administrators and members if there were any. They have to agree with the ones in /etc/groups. Now SRJ needs a directory. That should be old hat by now. SRJ also needs all the user login files. They're in a directory called /etc/skell for skeleton, /period. We'll give them to SRJ with CP-R for recursive. That all looks in order. Let's make it owned by SRJ. Shown recursively to SRJ with a group of SRJ, the directory /home/SRJ. Next, we set the permissions. Okay, that is chmod recursively. User gets read and write permissions. Group and others get read. And set all directories scannable. Looks good. Last step, SRJ needs a password. Fill in the password twice, and we're done. Exit out of our super user shell. SU to SRJ. CD to his home. That works. And it's not just for terminal accounts. I can log in with the GUI too. Note that the username is what I put in the name field in /etc/password. And here we are. SRJ's backgrounds aren't set up for video, so they look a little weird. Login as JRS. We can remove SRJ a lot easier using the script. Adding him back with the add user script is easier too. Give it a password. Fill in the blanks. Yes, done. Root. One name for many things. By now, you've heard me bandy about root shells, root privileges, the root of the directory tree, and a lot of other things that use the word root. This video is about what that actually means. Root is account 0 and group 0. It is the first account created when the system is installed. Without an account to own everything else, the entire Linux security model falls apart. Root owns most of the files on the system. It owns the kernel, it owns init, and upstart or systemd, whichever you use. This is critical since all processes started on the system's behalf are started with root privileges and then SU themselves back down to the level they need. They can't go back. All privileges flow from root. Any program that must run with enhanced privileges gets them ultimately from root. Even other privileged accounts, if created, must ultimately be in root's group, and so are using root's privilege. The root of the directory tree, / is certainly owned by root, and only root can write to it. It must be there for the system to function. This, in fact, is called the root file system, / plus /bin plus /sbin, and so on. Some Linux systems actually have a subset of the main root file system, enough for the kernel to boot, plus software for managing RAIDs and LVM drives. This root subset can be loaded as a RAM disk at boot time, so that the full root file system can live inside one of those more complex drives. Other than that, the root account has little to do with the root of the file system. The root account has its own home directory, and it's not /, it's /root. Chrooting is the act of changing the root file system while the system is running. While often used as part of a larger security system, by itself, it simply alters the environment the existing processes and the kernel are running in for whatever reason. In the Android world, this is used to wrap a normal Linux user space, utilities, compilers, and so on, around a running Android kernel to take advantage of the kernel's proprietary drivers without the rest of Android getting in the way. The root account is the only one that can log in and take action when the Linux system is running in single user mode. When it logs in, it runs with the usual absolute privilege, usually to repair some file that is keeping the system from booting past the single user stage. Because so much of the system flows from root, because root's level of privilege is so absolute, and because it's a handy single-syllable word, root privs is shorthand to describe the superuser level of privilege. A root shell, then, is a command shell like bash running with root privilege. To root a system, or to run a rootkit on it, is to acquire root privileges on the system through some exploit or other illicit means. When applied to Android and similar handheld computers, rooting the system is the act of taking control of root from the manufacturer of the device by the owner, who arguably should have had it in the first place. The truth is, root is a term that's grown fuzzy over the years because the root account, root processes, file system root, and the root of privileges all overlap, and everything ultimately goes back to the cluster of meanings behind the one word, root. Boot cycle, when it works right. Up to now, I've talked about Linux as a running system with all its parts in place. It's boot time. This video is about how Linux pulls itself together and becomes the operating system we know and love. I should mention that these mechanisms are generally present on PCs, although every distribution handles boot up a little differently. And when you get to the non-PC world, like the Raspberry Pi, whole stages may be missing entirely. The first thing that happens is that the BIOS or UEFI system initializes the hardware, determines which volumes have boot information on them, and which ones it should try to boot from. Once it determines that, it loads the bootloader. In BIOS systems, booting from master boot records, there isn't enough space in the MBR to put the whole bootloader, so this may take several stages. UEFI can do it all in one gulp. Regardless, the bootloader presents a menu, unless it's configured not to, allowing the user to select a kernel setup to load, or to boot to recovery mode. If nothing is done, the bootloader loads whichever kernel and configuration is the default after a few seconds. For PCs running modern Linux, bootloader is almost always grub, or Grand Unified Bootloader. The bootloader loads the kernel and transfers control to it. Once the kernel starts, things start to happen. The kernel sets up its interrupts, a mixture of software and hardware that allows devices and software to call kernel commands. Then it extracts the init ramfs mini root file system into its file system cache. It needs these because it's about to start the first piece of software. That first piece of software is init or systemd, depending on your configuration. Ubuntu, as of this writing, uses init, but systemd is coming, so we'll call it systemd for the sake of argument. Systemd loads the modules available in the init ramfs, giving the kernel new capabilities, most particularly to see and deal with logical volumes, RAIDs, and so forth. Systemd also launches udev at this point, populating the /dev hierarchy. Systemd isn't done by any stretch. Once all the modules are loaded, it unmounts init ramfs and mounts the real root file system in read-only mode. It then loads a new version of itself from the real root file system, along with new config files. If you're running Ubuntu 14.10 or earlier, this is where init starts upstart. And mine, they both run. Now that we have our full systemd and its configurations, and remember, I'm using systemd to stand in for init and upstart both, systemd loads more modules. Then it fscks the root file system and mounts it read-write. Systemd starts literally everything else: daemons, servers, internet service, and so on. Its final boot time action is to start a display manager, in Ubuntu's case, LightDM. This controls the graphical head, or the screen and the keyboard and the mouse. At this point, the system is up. You can SSH into it from another computer, and it will talk to you normally, which is really important for debugging. Once the display manager starts, things start looking normal on the screen too. The display manager, LightDM in this case, loads its global configuration files, then loads the configuration files of whatever the default account is, the last one logged in usually, and starts the X server based on those configurations. The X server is the Windows server of the system. We get the wallpaper of our default account, and all that's left is to authenticate, that is to give the password. Once I do, my desktop manager, Unity by default in Ubuntu, but it can be GNOME or KDE or whatever, starts up, and my desktop appears, and I'm in. That's very pretty, but what does it look like? And how could you tell if it worked right? It's in vogue these days to hide the output of all these steps, and small wonder. They go by too fast to see on a modern system, but they're all carefully logged. I've pulled the log files from my desktop Linux machine so we can look at them. Virtual Linux machines have strange lives and their boot cycles are weird. This is kern.log, the kernel's log, from the moment it was started by the bootloader. Here's the version, the command line that called it, and what kinds of CPUs it supports. That UUID is my real root partition on that machine. Here it's setting up memory with information from the BIOS. Here's the kernel unpacking the init ramfs. And here's the mount of the real root file system down here underneath all these device detections. And here it's finished FSCKing and is remounting the root file system read-write. Here's my graphic card driver loading. And here we start the display manager LightDM. Start the network here, but our link, Ethernet, isn't ready yet. And down here, Ethernet comes up, so IPv6 is ready. Here's the lightdm.log. Here we're reading information about the accounts. Apparently I hadn't deleted SRJ off my desktop machine yet. I have since. This is the kind of thing that non-privileged accounts need to access /etc/password for. Here's the authentication. I'm set to log in automatically, and we're in. Dmesg and Logfiles. In the days before Linux, when Unix ran on proprietary hardware the size of file cabinets in an air-conditioned room, there was one fixture every Unix machine had, a console. Toward the end of that era, this was a video terminal, like a VT220, but far later than you might imagine, there was an even older school printing terminal with a big box of paper in the front and an enormous stack of printed paper behind it. This was the console log. If something bad happened to the system, you paged back through that enormous mass of paper to find out what. Paper was cheaper than disk space. Thankfully, that's not how it's done anymore. Linux does keep track of what's going on almost obsessively through a combination of log daemons and logs and files hidden away in the file system. There's also a system called Dmesg, which lets you look at these console messages and much more on any terminal. In this video, we'll talk about Dmesg and log files and how to read log files and how to maintain the logs. So, what exactly is a log file? It's a file with usually text messages generated by some program while it was running. Usually they're from the kernel or daemons or other background processes that don't have any way to talk to the user directly. A log file has a number of uses. They're extremely useful for diagnosing system problems, especially subtle ones that only pop up periodically. They can be forensic information if something bad has happened, a process has run amok, someone broke in, and so on. Logs have various levels set by each daemon and by the kernel for how much information they produce, and they may change levels depending on what they're doing. Kernel, for example, will switch its log level to 7 during boot time, which includes all event levels below but not equal to 7. Once it's booted, it drops to 4. The lower the level, the more urgent the messages are. Emergencies are 0. They will always be logged. Fortunately for system administrators, applications and daemons aren't responsible for creating their own log files. They used to be, and logs wound up everywhere. Today, there's a daemon for that called rsyslogd. rsyslogd is configured by the /etc/rsyslog.conf file with rules in the /etc/rsyslog.d directory. The former specifies the behavior of rsyslogd, and the latter tells it what logs should go into what files and which it can ignore completely. rsyslogd does not clean up after itself. Left to its own devices, it will entirely fill the file system it's in. This is something to watch out for, particularly on small file systems like those on Raspberry Pi. Instead, cleanup is handled by a program called logrotate, which in turn is run by a daemon called cron. Cron is a daemon that monitors the time and runs jobs on a fixed schedule. The cron job for logrotate calls the logrotate program and runs its default configuration, which is found in /etc/logrotate.conf. Logrotate closes the log files and opens new ones. It can also be configured to compress a range of older versions and erase the oldest logs. As for the log files, they're almost always located in /var/log or a subdirectory thereof. What logs are available varies from Linux distribution to Linux distribution. But here are the logs in this virtual Ubuntu machine. Identifying them can be a little tough at times, but when you use a system for a while and you know what programs have been run, you'll often recognize the log titles. This is Ubuntu, so it's got a lot of dpackage logs. Dpackage is the installer, or one of them. Kern.log is the kernel log. You can see logrotate has had its way with it. There's kernel log 1, 2, and 3 and 4 have been compressed. LightDM is the display manager for Ubuntu, so the LightDM directory contains LightDM's logs. A lot of logs may be empty from software that used to be on your Linux system but isn't anymore, or that nobody uses. Logs can be thousands upon thousands of lines long, especially superset logs like syslog, which contains all of kernlog and a lot more. Usually when something happens, you want the most recent few lines, and more starts at the beginning. The command for this job is tail. Tail prints the last 10 lines of a file. If you want more, you can pass tail a number as a flag. If you want to watch the logs as generated, you type tail -f kern.log. Every time there is an event, It will be written right here as soon as it's written to the file, until we press Ctrl-C. Actually reading the logs is an exercise in patience. You can pipe it through grep for certain events, you can edit it if it's small enough in your favorite editor, and search it that way. Most of the time, if something happens in a system, there's a log of it and the truth is in there. Remember all those console lines that go by so fast you can't read them, and most Linux systems don't display them by default anymore? You can get those back. The command is dmesg. There it is, the full startup console log. Dmesg pulls it straight from the kernel's log area, even as the kernel writes it to kern.log with rsyslogd. So dmesg will catch messages that go by if rsyslogd isn't running yet. It has a lot of options, well documented in the man page. Dmesg can give you messages from any facility, the kernel, users, authorization, printers, even Usenet if your system feeds it. And of course, there's a log file of all the dmesg messages in /var/log. Linux is tough, but sometimes bad things happen to it and it just won't boot. As the system administrator, it's your job to fix it. But stop and think a moment. Linux is a system. Booting is a sequence of events. Each event that still works limits what the problem could be. Booting follows a path. Follow that path. It's a tough business, but it almost always starts in the same place: hardware. Debugging hardware. Here's an approach to debugging hardware. Take a step back and think for a moment what exactly Linux really needs of its hardware in order to boot. The hardware will need power. Seriously, check to make sure the computer is plugged in. It works better that way. Laptops, this applies double to you. Get the system working right, plugged in, before you worry about the battery. Are the keyboard and mouse and screen connected? Again, seriously. Is your RAM showing up in the amount you expect? Look in your BIOS settings, if your system has any. UEFI, same game. If you're seeing a different amount of memory than you know you have in the system, something's amiss. DIMMs go bad sometimes. Some fans and PCs are mission critical. Without them, the BIOS will shut the system off to protect expensive hardware. CPU fan, graphics card fan, power supply fan, and check the rest of them too. The BIOS UEFI configuration needs to be right. Is your system trying to boot from the right volume? Did you perhaps change the motherboard from a BIOS one to a UEFI one without setting Linux up for it first? Might want to put the old one back in if it still works and set Linux up to deal with UEFI. Okay, hardware checks out. That's good. That means the problem is on the boot volume someplace, because that's what has to work next. There are lots of ways to get at the boot volume on a system that won't boot. Rescue flash keys, the install disk, or my personal favorite, plug it into another Linux system. These all give you a full interactive Linux environment, a GUI, a web browser. It's the way to go if you can. Just be careful, and make sure you're talking to the device name you want, and not the second machine's root file system. The only thing worse than one broken Linux machine is two. So imagine we've connected the root file system from our broken Linux machine to our good one. I've installed a flash key on this system to masquerade as that drive. There it is. Missing a partition? We are now. Parted has a rescue mode. We need to switch our units to sectors and get the sector numbers where the partition was. I know the partition was the second partition and that it went from the end of the first partition to the end of the drive. Okay. Command is rescue. Fill in the beginning and ending sectors of the hole where my partition was. It found it. Yes, we would like to re-add it. Done. We auto-mount them. Test file is present. And the file works. Let's make sure, though, that the file system wasn't damaged. We'll use FSCK. FSCK stands for File System Check, and there is one huge gotcha about using it. Don't ever, no matter who advises it, point FSCK at a writable, mounted file system. It will wreck the file system. I'm sending FSCK two flags, -F for force. We don't care whether FSCK thinks the file system needs checking or not. We want it to be checked. -T lets us specify the file system type. If FSCK reports only a few errors and asks to fix them, say yes. If you get hundreds, the file system is probably lost. File system checks out, Great, it's a software problem. Did Grub start? Your install DVD or flash key probably has the tools to fix that, but you want to do it on the system the volume belongs in. Otherwise, it's time to open up a terminal window and do some digging. Check the logs. Is permission denied being thrown around? ls-l, ls-ld, and chmod are the tools you want. Make sure you check the directories too. Permissions on a directory can be wrong, and it can make a heck of a mess. Whatever happened, the logs stop abruptly somewhere. They tell you where things became untenable. You can edit files, tinker with permissions, replace missing files, or retrieve all the valuable data off the volume and reload if you're on a second system. If you don't have a flash key or another computer, but Grub is working, you can start recovery mode. In the Grub menu, select Boot, your kernel, recovery mode. If you know one of the other tools listed relates to what happened, try it. Otherwise, go to Advanced Options and select Root Shell. This is single user mode. The only difference between it and a regular root shell is that your file system is mounted read-only. You can FSCK it at will. File system checked out? Awesome. Remount the file system read-write so you can change things. That's Mount -O for options. We want the remount option, and we want it RW for read-write. Now you can use the same methods I already showed you to try and fix things. Boot failure is usually because something drastic happened, and drastic changes are the easiest to detect, if not necessarily to fix. I can't tell you how to fix everything. There are too many ways for it to break, but if you keep in mind that Linux needs X to boot, has it got it, check, move on, you can often sort it out. It happens to everyone sooner or later. You're working along, and all of a sudden, the screen stops responding. No typing, mousing, or anything will bring it back. For me at least, this usually happens right before I was planning to save whatever it is I was working on. You're the system administrator. What do you do? With any hang, the goal is to recover whatever you were doing if possible, and then get the system working again. Stuff happens. A hang can be some interaction between 5 or 6 pieces of software that only happens every 30 years on average, or it can be a recurring problem because something has changed. The first step in resolving a hang is knowing what kind of hang it is, a GUI hang or a system-level hang. There's an easy way to tell. If the caps lock key works, and the light goes on and off normally, then the kernel at least is running and it's interruptible. If not, the kernel is down, and resetting or power cycling it is your only option. You did check that the keyboard is still connected, right? Right, I thought so. The military has a saying, once is happenstance, twice is coincidence, and 3 times is enemy action. Somewhere around 2 or 3 hangs in a row in a short period of time, it's time to find out why the system isn't stable. When I see random crashes and hangs where the kernel is stopped, my first suspect is usually the power supply. If the machine is a Raspberry Pi, it's almost always the power supply. If a logic voltage supply sags, the system can go off the rails with no warning. It's more likely when you plug something into the USB port or you've added a new card, especially graphics cards. Memory is my second favorite suspect, especially if I've added any recently. RAM is usually like light bulbs, or the old filamental kind. They either fail in the first week or so, or they work for years. I'm not an overclocker, so heat is only my third suspect. If you notice your system hangs after a few hours, or more in the summer, or when the furnace is running, you might have a thermal problem. The LM Sensors package can give you basic readings on the motherboard, and even proprietary graphics drivers usually have some way of checking the temperature of the card. If your file system's corrupt, it can cause a kernel hang, and so can bad or corrupt drivers and kernel modules. But usually you'll see these as a failure to boot at all. If kernel hangs always happen after starting a specific piece of software, you may want to keep file system problems in the back of your mind and force a file system check on your next clean shutdown. If the caps lock key does work, it means the kernel is interruptible. It's listening to the hardware and doing its job. Try pinging the machine from another machine on your network. If you can get a ping back from your Linux machine, awesome. Even if you can't, try logging in with SSH. I always recommend installing SSHD when you set a system up for this reason. You can get SSH clients for your phone if you haven't got any other computers. If you can get in with SSH, you may be able to see the problem with top, PS, vmstat, and the usual tools. You can reboot from there, but you might want to think about sending whatever programs you were running a polite kill -15, so they can do an emergency save if they're so inclined. Most Linux native apps will, and you can get your work back. Having done that, you can restart the GUI on your system by finding the display manager and sending it a kill -15. If that doesn't work, send it a kill -9. Once it's gone, restart it. The command is right there in your PS output. If your GUI comes back, great. If not, do a clean reboot. Sometimes your network won't work even though the kernel is still responsive. Try a Control-Alt-F2 to see if you can get a terminal. It looks like this. You can use Control-Alt-F7 to exit from this terminal. If not, there's still a way to restart the system cleanly. It's called raising the elephant. In the Linux console system, there's a mechanism called magic sysrequest keys. Limber up your fingers because it's a stretch. To raise the elephant, hold down the Alt key and the print screen key and press, in this order, all lowercase, R, E, I, S, U, B. Raising the elephant is from the mnemonic for these keys. Raising elephants is so utterly boring. The R key changes the keyboard mode and takes it away from X Windows control. E sends a sig term, kill -15, to all processes. Might want to give this some time to work, at least until your hand starts to cramp up. I sends a kill -9 to any surviving processes. S syncs the file system, clearing the caches and preparing for shutdown. U remounts the file system's read-only, and B reboots the system right now. Again, the kill -15 gives any apps that are still running the chance to do an emergency save, so you can recover that video script you were writing when the system reboots. This video is about how to approach the problem of no GUI. As we reach the graphical user interface level of things, everything becomes distribution specific and version specific, so there's not a lot of specific advice to give. What I can give is an approach and what kinds of things to look for. The good news is that modern GUIs don't fail very often, and when they do, it's usually from some user intervention. But still, check to make sure everything's plugged in. Tearing a system apart to discover that something's not plugged in, it's embarrassing. As always, when faced with a GUI problem, my first instinct is to look for a terminal. Do I have one on the screen? Can I get one? If I have one, what terminal environment is it? There are a number of possibilities. If the system didn't finish booting, there's a good chance I'm looking at the single user environment. This is a boot problem, and they're covered in another video. If there's a login prompt, try it. If it works, you've got something. If you can SSH into the system from another machine, by all means, do that. Then you'll have a terminal and a web browser, and you'll need both. The GUI environment evolves quickly, and most of the documentation for it is going to be online. Before we peek into the insides of the GUI system itself, there are things to consider. Where is the GUI failing? Does the login screens window change to the account wallpaper? That's the handoff from the display manager to x.org and the desktop manager. If it's dying there, it might be some of the config files in the user's account. There's an easy way to check if you're not automatically logged in. See if you can log in as another user. If you can, it means the deeper innards of the GUI system are working. If you are automatically logged in, look up how to turn that off. In Ubuntu, it's in the /etc/lightdm.conf file. If there is no other user, you can add one with add user and remove it when you're done. Copying config files from this new user after starting the GUI for them to make sure it works might be one way to solve the problem. GUI innards. Broadly speaking, there are some basic things your GUI system has to have. This list assumes you are using an X Windows-based GUI. There are others in the pipeline, and all of this may have changed. Like I said, not a lot of specific advice here. Most of the time, the deep innards of the GUI aren't casually altered, nor should they be, but there are some basics to check. There's an option in /etc/default/grub to disable the graphical terminal and force Linux to boot to the command prompt. It's called grub_terminal = console, and it should be commented out. There's also a grub setting called grub GFX mode, which should either be commented out or set to something your graphics card understands, and so on. Some Linux bootloaders pass parameters to the kernel too. These need to be correct for your installation and your version of Linux and your hardware. Make sure that if you change the grub config files to update grub, the script for this is update-grub. Or you can issue the command directly with grub-mkconfig -o/boot/grub/grub.config. For me, the most common failure mode for my desktop Linux machine's GUI is that either I've upgraded the kernel and not upgraded the proprietary GPU driver, or I've upgraded the proprietary GPU driver and not the kernel, or my personal favorite, I haven't completely removed the default open source driver before installing the proprietary one, or I'm testing a new open source driver and it doesn't quite work. If you know you changed a driver, see if its installer has the ability to uninstall itself. Do some web searching. Search with the errors that are turning up in the logs. Ditto for the display manager. They're pretty robust, but they have config files that can get messed up. Check the logs for display manager messages. X.org is the X server itself. If it doesn't run when the display manager calls for it, you've got no GUI. All I can say about Xorg's config files is that they should be left alone. The bad old days when we had to set X windows up to run with video boards by hand are thankfully behind us. Dbus is an inter-process communications daemon, and most GUIs are heavily invested in it. If you're getting dbus error messages or other components complaining about not finding dbus, that's a place to look. Is the desktop manager running? That's Unity in Ubuntu, KDE or GNOME in Fedora, and so forth. Look up what your Linux machine uses and see if the processes are there. Look for messages that come from them in the log files. If worst comes to worst, your command line software installer probably is capable of reinstalling the whole GUI system. Make sure that when you look the instructions for that up online, you get the ones that work with your version of Linux. This should be a nearly last resort approach, as the probability of making a bigger mess is quite high. Bad things happen to good file systems. Modern journaled file systems like ext4 are far more resilient than the file systems of just a few years ago. But even so, sometimes an errant program will make a mess during a write. Hardware will crash at just the wrong moment, or your volume or its driver might be just a little bit flaky when you overclock. Raspberry Pi SD cards, I'm looking at you. When that happens, if the damage isn't too bad, you can usually fix it with FSCK. That's what this video is about. So, how do you tell if your file system is corrupt? There are some obvious symptoms. Files won't open, data comes out garbled, programs crash when they used to work, the dates on ls-l have gotten set to the 1970s, permissions are mangled, and the list goes on and on. The most common way to discover file system corruption, however, is that the FSCK the system does at boot time complains. If it tells you errors were found, or worse, stops the boot cycle until you fix them, you need to do something about it. If it's your root file system that's throwing errors, that something had better include booting from another physical volume so you can actually fix the errors. I've said it before, and I'll say it again. Don't point FSCK at mounted running file systems. Really, if it works at all, it will trash the file system. However, in another video, you may have noticed that I said init/systemd does exactly that, while the root file system is mounted read-only. You might have also wondered how exactly FSCK fixes file system problems on a read-only file system. This is how. FSCK has two functions. One of them is to check the file system. If the file system is mounted read-only, this one will work fine, and if there's nothing wrong with the file system, it will tell you, and you can go on your merry way. You can enforce this with the -n flag, or FSCK will figure it out for itself if you point it at a read-only file system. Otherwise, FSCK can also write and will ask you whether you want to make repairs. You can't repair a read-only file system. The system won't be able to write to it. If you remount the file system read-write, and the system tries to write to the file system while you're repairing it, the results are unpredictable and destructive. FSCK versus E2FSCK versus FSCK.ext4. This is another point where things aren't very clear. In the old days, FSCK was the tool, and that was that. The way things are now is that FSCK itself is a front end for E2FSCK, and FSCK.ext4 is a symlink to E2FSCK. We'll use FSCK itself because it covers the broadest number of file systems. You should also know that some file systems do not support FSCK. All the current ones through ext4 do, but the more exotic ones sometimes don't. If you're using something besides ext4, check this before you bother with FSCK. FSCK flags. As usual, there are a myriad of flags that FSCK understands. I'm only going to cover a few of the most common. The rest are in man FSCK and man E2FSCK. And remember, they can be different. No repair. Don't try and fix anything, just tell me if it's broken, is -n. This isn't universally supported, by the way. Some file systems will report no errors, even if there were any, and some will reject the flag entirely. Automatic repair, -A or -P. Not everyone is a file system expert. If you know what the error system's FSCK was giving you mean, you can make decisions about whether to fix them. If the file system doesn't work and it's FSCK or throw it away, use the -A option. This will tell FSCK to do its best to fix all the problems. If the file system works after that, count your blessings, but don't count on the files being right. -P is an E2 FSCK flag that automatically fixes a list of easy-to-fix problems, but leaves more complicated problems alone. -T allows you to specify what kind of file system you'll be repairing. Probably a good idea if the file system is badly messed up, as FSCK might not be able to tell. -F stands for force check. If a file system was unmounted cleanly, it means the cache was properly flushed and all the data should be in the file system, and the dirty flag should be cleared. FSCK will exit immediately after telling us this fact. If you want it to run anyway, use the -F flag. I've installed a flash key on this virtual machine to demonstrate FSCK with it. So, we'll unmount the partition and FSCK it. It's clean, so no check was run. So we force the check. This is the kind of output you always want to see. Completely clean, no problems. FSCK will sometimes deposit files that were missing directory entries in the lost and found directory. Nothing in there this time. I took quite some trouble to make a mess of the second partition on this flash key using a tool called DD. I tried to copy a partition from a 932 GB rotary drive onto a 900 MIB partition of the flash key. Didn't work. It's there, called target. And we get lots of errors. It's doubtful we'll ever get anything coherent on this file system again. That's part of the art of using FSCK. We can run it again and again until it builds something that will mount, but if anything will be useful on that file system is impossible to say. I recommend using FSCK to fix small things. When a file system has this many errors, it's not useful anymore, and the data is not trustworthy anyway. I used to run PC Unix systems in a wafer fab at a semiconductor manufacturer. We had 10 minutes to fix problems. If it took longer than that, we yanked the drive and replaced it. If that didn't get it, we pulled the whole machine off the wall and replaced it. Tool time was far too valuable to spend the afternoon debugging a recalcitrant Unix system. It's a philosophy I've carried with me ever since. At some point, it's easier to reinstall. This video is about deciding when to pull the lever and start over, and how to make it hurt less. So, how do you tell when it's time? First of all, you have backups, right? Seriously. If you have full dump backups, restoring from them should take just about as long as making them did. If you're applying a backup and then a bunch of deltas, lists of files that were changed, it's a different calculation. Has your boot volume failed? No question, you're good for a reinstall. Just one partition of it? Maybe. Have you been seeing bad FSCKs on your root file system or on any other file systems on this device? I would replace the device, and yes, that's reinstall time. How old is this installation? And how much have you installed, removed, and tinkered with it? There's something to be said for a fresh, clean installation. You know that the weird problems you do encounter are probably the same ones others have had, instead of something unique to the system and its history. Upgrades are not always smooth. And then there's the question of trust. Do you depend on this machine to do useful work? Will it be worse if it goes down again later, maybe while you're away? Another question is, are there other operating systems on this volume? If so, the state of your boot matter suddenly matters quite a lot, even if this Linux install has had it. Does the bootloader still load your other operating system? Lots of questions and value judgments for the system admin to make. While we're on the subject of backups, let's talk a little bit about what to back up. Definitely back up your /home directory, or partition, or logical volume. That's the stuff you'll miss the most. If you have a major database or some other application running that is mission critical, you know better than I how much that needs backing up, and how regularly, and how to do it. It's definitely not safe to assume that a database can be backed up live, or even shut down, its disk unmounted, and copied. It might work, it might not. The database software will have a backup method. Use that. Likewise, major apps may have custom groups, accounts, and drivers. Whether they'll even work restored from backup depends on how the backup was taken and what the apps require. Reinstall or restore? You have to make that decision. Whether you should back up the root file system is a different question. They're not hard to build. A lot of the time, they're pretty much the way they came out of the box. Do you really need to back that particular one up? That's something you, the system administrator, have to decide. Is there anything special about this kernel? Did you build it yourself? Or is it the generic one the installer put in? Are there licenses involved? Do you have the keys? You should. Making reinstalls less painful next time. If you do decide to reinstall, I have some suggestions of things you can do to make it less painful next time. If you haven't installed yet, or the system is still running, think about these things for future catastrophes. Move /home to its own file system. This single thing makes most reinstalls a lot less painful. If there's nothing else unusual about the system, a reinstall is just a matter of loading the system up, logging into root, and rebuilding your account. Set the user and group IDs to the same as the old ones, point the new account at your old home directory, and you're good. If you've installed all your software through Debian's dpackage, or apt-get, or Fedora's yum or something similar, you can probably generate a list of all the software you've installed. For Ubuntu, this is how. For Fedora, that. Keep these lists handy, maybe in your home file system, and you can feed them to the installer when you reload and get all the software you installed before without having to remember it all. Above all, think about what's necessary. Reinstalling is a good time to prune out stuff you don't use anymore. For me, at least, watching the list of files go by as I restore my home directory is embarrassing. It reminds me what a digital pack rat I really am, and that I'm spending time and drive space storing this stuff. A reinstall, whether deliberate or to repair a broken system, is a fresh start, a time to apply what you've learned since the last install. Want to switch to a pure logical volume management system? Reinstall is a good time for that. You're already doing most of the work. Hardware upgrades? No better time. Letting the installer sort out the drivers is the easiest way to go. Reinstallation is not the end of the world. It's a new beginning for your Linux computer. There's one more thing to do when you're done with the system. One more command. Shutdown is the terminal environment's equivalent of the logout shutdown button in the GUI. It tells the system to do a clean shutdown, stops processes, syncs and dismounts the file systems, and takes the system down to single user mode by default. But it can do a lot more. Shutdown takes several flags, and as usual, I'm only going to cover a few of them. -R reboots the system. -H halts, and on most PCs, powers the system off. -F sends the -F parameter to FSCK on the next boot, forcing a file system check. Shutdown also takes a time parameter, which can be an absolute time in hours and minutes, or now, and a message to tell all users. And that's a wrap. So here we are at the end of the series. Let's take a moment to review the topics we've covered. We've covered the terminal environment, how to use it, how to use its power tools like regex, sed, grep, pipes, redirects, and how to enable superuser or root privileges. We talked quite a lot about what files and directories are and how they originate in the inode tables. We covered the file system in general, and we talked about all the virtual file systems like /dev. We talked about partition tables, logical volume management, and the venerable but still useful FSTAB file. We talked about the kernel and some of the services it provides, processes, virtual memory, file security, and the tools for checking up on and manipulating all those things. We went into some depth discussing account anatomy, so you can fix accounts when they break, as well as create and remove them. And we talked about exactly what root is, because the word has so many meanings. We talked about how the boot cycle is supposed to work, how to read Dmesg and Logfiles, and discussed some strategies for dealing with various failure modes, like when the system won't boot or the GUI hangs. Finally, we talked about when it makes more sense to stop fighting the good fight and reinstall Linux, and how to make that a little less painful. The most important concept to remember is that in Linux, everything is a file. If there's one concept that's absolutely fundamental to understand about Linux, it's that. Files and inodes are the interface to everything else. Whether they're real files, all 332,072 of them on my virtual Ubuntu machine, or virtual files like the contents of /dev and /proc. Files are the abstraction around which Linux and all other Unix operating systems are built. What I hope you've gotten out of all this is, like I said in the introduction, a handle on the fundamentals of how Linux systems work, what the controls are, and how to apply them so you can take control of the machines that serve you. I hope I've given you the place to start. On behalf of myself, thank you for watching.